Hello there, and welcome to Science for Sleep, a quiet place where curiosity slows down, explanations take their time, and big ideas are allowed to stretch out gently instead of rushing past. Wherever you happen to be listening from tonight, whether the lights are already dimmed or the room is still settling into evening, I'm glad you're here. This is a space meant for winding down, for letting your thoughts loosen their grip a little, while science continues softly in the background, like a calm voice you don't have to answer right away. Tonight we're easing into a question that sounds enormous the moment it's spoken, but doesn't need to feel overwhelming. We're going to explore how big the observable universe really is. Not in a sharp, startling way, not with sudden jumps or dramatic declarations, just slowly, carefully, letting the scale reveal itself piece by piece, the way your eyes adjust when you step outside on a clear night and look up. When people hear the word universe, it often comes bundled with a kind of mental vertigo, numbers too large to picture, distances that refuse to fit inside language. It can feel like trying to imagine the total number of grains of sand on every beach, multiplied by something that doesn't have a name yet. But the observable universe is a slightly different idea. It's not everything that exists, and it's not a claim about the ultimate size of reality. It's simply the part of the universe that we can in principle see, the portion that light has had time to reach us from since the universe began. That distinction matters, and we'll spend plenty of time with it later. For now, it's enough to let the phrase sit quietly for a moment. The observable universe, a region defined not by walls or edges, but by time, motion, and light. A kind of cosmic bubble centered on you, no matter who or where you are, simply because observation always begins from the observer. Before we drift any farther into that idea, take a second to notice where you are right now. What time is it where you're listening from? Late evening, perhaps? Early morning? Somewhere in between? Maybe the world outside your window is quiet, or maybe it's still humming along, unaware that you've stepped briefly into a much larger story. And wherever that place is, on whatever continent, under whatever sky, it sits inside the observable universe too, carried along with everything else. If you find this kind of slow exploration soothing, or if you enjoy letting large questions unfold at a pace that doesn't demand anything from you, you're always welcome to like the video or subscribe to the channel. It helps this small pocket of calm reach other people who might need a gentle place to rest their thoughts. There's no rush with that either. You can always come back to it later. Now, instead of leaping straight into measurements and figures, it helps to start with something familiar. Imagine standing outside on a clear night, far from city lights, where the sky's dark enough for the stars to really show themselves. You look up, and at first you notice the brightest points, maybe a planet or two, a handful of constellations you recognize. As your eyes adjust, more stars begin to appear, fainter ones, clusters, a hazy band stretching across the sky that you eventually realize is the Milky Way, seen from the inside. That experience is already a lesson in scale. What you're seeing isn't a flat ceiling dotted with lights, it's depth, distance layered upon distance. Some of those stars are a few dozen light years away, others are thousands, and the faint smudges that look like clouds or soft glows aren't clouds at all but entire galaxies, each one containing billions of stars of its own. Even then, you're only seeing a tiny fraction of what's out there. Most of the observable universe is invisible to your eyes, not because it isn't there, but because it's too far away, too faint or emitting light. Your eyes weren't built to detect. Telescopes extend that reach. Radio dishes listen where eyes cannot see. Space observatories drift far above the atmosphere, collecting ancient light that has been travelling for billions of years before finally arriving. And that idea alone is worth pausing on. Light does not arrive instantly. It moves at a finite speed, incredibly fast by everyday standards, but not infinite. When you look at the moon, you're seeing it as it was just over a second ago. When you look at the sun, you're seeing it as it was about 8 minutes in the past. The stars you see at night may no longer be exactly as they appear. Some may have changed. Some may even be gone, their light still crossing the vast distances between. So when we talk about the observable universe, we're talking about a view that is also a history. The farther out we look, the farther back in time we see. There's no separate switch between distance and age. They are the same thing, woven together by the speed of light. That's why the observable universe has a limit at all. Not because there's nothing beyond it, and not because space simply stops, but because the universe has a finite age. There has only been so much time for light to travel since the beginning. Anything farther away than that limit exists beyond our observational horizon, not necessarily unreachable forever, but unreachable for now. The phrase edge of everything can sound misleading here. It suggests a boundary you could point to, a place you might eventually reach if you travelled far enough. But the edge of the observable universe isn't a physical wall, it's more like the farthest distance from which information has had time to arrive. A horizon, in the same way the horizon on Earth marks the limit of what you can see from where you stand, even though the land continues beyond it. As you settle into this idea, it's okay if the numbers don't fully register yet. They don't need to. Human intuition wasn't built to handle billions of years or trillions of kilometers. What matters more, especially right now, is the shape of the story. The universe has been expanding. Light has been travelling, and you are located at the centre of your own observable universe, simply because observation radiates outward from wherever you happen to be. That last part often surprises people. It can sound oddly self-centred at first, as though the universe is arranged around each individual observer, but it's not about importance, it's about geometry. Every observer, anywhere in the universe, sees themselves at the centre of a sphere of observable space, bounded by the distance light has travelled since the beginning. Someone in a galaxy billions of light years away would have their own observable universe, overlapping with ours in places, extending beyond it in others. So the question, how big is the observable universe, is quietly personal. It's a question asked from a location, from here, from now, from wherever you happen to be listening, breathing, letting your thoughts slow down. For now, though, it's enough to rest at the starting point. You're here, inside a universe that has been unfolding for billions of years, carrying light across unimaginable distances, quietly making it possible for questions like this to be asked at all. The observable universe isn't just a scientific term, it's a reminder that there is a limit to what we can know directly, and that within those limits, there is already more than enough to occupy the mind. When scientists use the word observable, they're being very precise, even if it doesn't always sound that way at first. In everyday language, observable just means something you can notice or see. In cosmology, it carries a much stricter meaning, one that quietly sets the limits on everything we can ever measure, photograph, or directly study about the universe. To understand it properly, it helps to let go of the idea that the universe is something sitting out there all at once, fully visible if only we had a powerful enough telescope. The universe doesn't work like a landscape waiting to be surveyed. It's more like a conversation that's been ongoing for billions of years, where information travels at a finite speed, and you only ever hear what has had enough time to reach you. That speed limit is set by light. Light is not just illumination, it's the primary carrier of information in the universe. When something happens far away, a star ignites, a galaxy forms, a cloud of gas collapses. The only reason we can ever know about it is because light, or some other form of electromagnetic radiation, carries evidence of that event across space. And no matter how advanced our technology becomes, that information cannot arrive faster than light travels. This is where the idea of observable begins to take shape. The observable universe is not defined by how far we can see with our eyes, or even with our best instruments. It's defined by how far light has been able to travel since the universe began. Anything beyond that distance may very well exist, but it has not had time to send us a signal yet. As far as observation is concerned, it is beyond reach. This immediately tells us something important. The observable universe is not the same as the entire universe. It is a subset, a region carved out not by physical boundaries, but by time itself, and that region grows as time passes because light from more distant places continues to arrive. Imagine striking a bell in a vast, dark field. The sound spreads outward in all directions, but someone standing far away won't hear it right away. Until the sound reaches them, the ringing might as well not have happened from their point of view. Light works in a similar way, except instead of seconds, we're dealing with millions and billions of years. This means that observation is always delayed. We never see things as they are right now. We see them as they were when the light left them. That delay grows with distance. Nearby objects are seen with short delays. Distant objects are seen as they were deep in the past. At extreme distances, we are looking back to the early stages of the universe itself. So when cosmologists talk about observing the universe, they are really talking about reading a record written in light. The observable universe is the portion of that record that has arrived so far. There's another subtlety hidden inside the word observable, and it has to do with perspective. The observable universe is centered on the observer. That might sound strange at first, but it follows directly from the way light travels. Wherever you are, light reaches you from all directions at the same speed. That makes your location the center of a sphere, defined by the maximum distance light has traveled since the beginning of the universe. If someone else were observing from a different galaxy billions of light years away, they would have their own observable universe centered on their position. It would overlap with ours in many regions, but it would also include areas we can't see and exclude some we can. There is no single, universal observable universe shared by all observers. There are as many observable universes as there are vantage points. This doesn't make observation subjective or arbitrary. The laws governing it are the same everywhere. What changes is location. Just as the horizon on Earth depends on where you're standing, the cosmic horizon depends on where you are in the universe. It's also worth clearing up a common misunderstanding. The observable universe is not limited by the sensitivity of our instruments. Even if we built a perfect telescope, one capable of detecting a single photon from any distance, the observable universe would still have a boundary. That boundary is set by time, not technology. In fact, we already observe light that has been travelling for nearly the entire age of the universe. The oldest light we can see comes from a time when the universe was very young, long before stars and galaxies existed. That light has been stretched and cooled by cosmic expansion, but it still reaches us, marking the current edge of what is observable. Beyond that, there may be more galaxies, more structures, perhaps an unimaginably larger expanse of space. But without information reaching us, science has no direct way to confirm or deny their existence. Observation stops there, even if reality does not. Another important point is that observable does not mean visible in the ordinary sense. Much of what we observe in cosmology is invisible to human eyes. We observe radio waves, microwaves, infrared light, ultraviolet light, X-rays, and gamma rays. All of these are forms of light, carrying information from different physical processes across the universe. So when scientists map the observable universe, they are not just creating pictures, they are assembling data from many wavelengths, each revealing different aspects of cosmic history. Hot gas glowing in X-rays, cold dust shining in infrared, ancient radiation lingering as faint microwaves. Together, these observations form a layered view of what has happened within our observational horizon. The word observable also carries an implication of humility. It acknowledges that our knowledge has limits, not because we lack intelligence or effort, but because the universe itself places constraints on what can be known from any single point in space and time. This idea can feel unsettling at first. There's something deeply human about wanting the whole picture, the complete map. But the universe doesn't offer that to anyone. Every observer is embedded within it, receiving information at a finite pace, forever surrounded by regions that remain unseen. At the same time, there's something quietly reassuring about this limitation. It means the universe is not something finished and static, waiting to be fully catalogued. It's something unfolding. The observable universe grows as time passes, as more light arrives, as more of cosmic history becomes accessible. Even now, light that left distant galaxies billions of years ago is still on its way. Future observers, billions of years from now, will see a different observable universe than we do, assuming the universe remains transparent enough for that light to reach them. Their cosmic horizon will include regions that are invisible to us today. Of course, the expansion of the universe complicates this picture, and we'll take our time with that later. Expansion means that not all light will eventually reach us. Some regions are receding so quickly that their signals will never arrive. But even this fact is folded into the definition of what is observable at any given moment. Right now, observable means has already reached us or can reach us in principle, given the universe's expansion history. It's a dynamic boundary, shaped by cosmic conditions, not a fixed wall. Another subtle point is that observation does not require a conscious observer. The universe does not care whether someone is watching. When cosmologists say something is observable, they mean that information from that region can, in principle, interact with detectors, instruments, or matter at our location. Whether or not anyone is actively paying attention is irrelevant. This distinction matters because it separates observation from perception. The observable universe is not defined by human awareness. It's defined by physical interaction. Light arriving here can heat matter, trigger chemical reactions, or be absorbed by detectors, regardless of whether anyone looks at the data. In that sense, the observable universe is a physical concept, not a philosophical one. It's grounded in measurable processes, even if it raises deep questions about knowledge and limits. As you sit with this idea, it can be helpful to think of the observable universe not as a container, but as a growing archive. Every moment new entries are added as light from distant regions finally reaches us. Some entries are ancient, recording events from the universe's earlier stages. Others are more recent, reflecting ongoing processes in galaxies relatively nearby. And just as any archive is incomplete, shaped by what has been preserved and what has been lost, the observable universe is shaped by what light has survived the journey through expanding space. Some signals fade, some are absorbed, some are stretched until they are barely detectable. Observation is always filtered by the medium it travels through. This filtering does not make observation unreliable. It simply means that understanding requires care. Scientists spend enormous effort accounting for these effects, correcting for distortions, and separating genuine signals from noise. The result is not a perfect picture, but a remarkably consistent one. Within the observable universe, the same physical laws appear to apply everywhere. The same patterns repeat. The same types of particles, forces, and interactions show up again and again. This uniformity gives scientists confidence that what lies beyond the observable horizon is not radically different, even if it remains inaccessible. But confidence is not certainty, and science draws a clear line between what can be inferred and what can be directly observed. The word observable marks that line. As we move forward, this definition will become increasingly important. When we start talking about the size of the observable universe, we are not making claims about the ultimate size of all existence. We are describing the scale of the region that has made itself known to us through light and time. That region is already vast beyond easy comprehension. It contains hundreds of billions of galaxies, each with billions of stars, each star potentially hosting planets. And yet, by cosmic standards, it may be only a small patch of a much larger whole. Understanding what observable means allows us to hold both ideas at once without confusion. We can appreciate the immensity of what we see, while remaining open to the possibility that there is more, far more, beyond the horizon we cannot yet cross. There is a reason the universe feels so vast even before we begin attaching numbers to it. That reason has very little to do with how much space exists, and everything to do with how fast information can move through that space. At the heart of the observable universe lies a simple but deeply consequential rule. There is a maximum speed at which anything can travel. Nothing, no matter how energetic or exotic, can move faster than light. This idea is so familiar now that it can sound almost ordinary, but it is one of the most important limits in all of science. It shapes not only how the universe behaves, but what parts of it we're even capable of knowing about. Without this speed limit, the observable universe would be a meaningless concept. With it, observation becomes a matter of patience, distance, and cosmic history. Light moves incredibly fast by everyday standards. In a single second, it can circle the Earth more than 7 times. In the blink of an eye, it crosses distances that would take a commercial airplane years to traverse. And yet, when set against the scale of the universe, even this astonishing speed turns out to be finite, restrictive, and defining. To appreciate what that means, it helps to slow the idea down rather than rushing past it. Imagine that the universe has just begun. Space exists, energy exists, and light begins moving outward in all directions from every point where something happens. But it does not fill the universe instantly, it spreads, like ripples on a pond, except the pond itself is stretching at the same time. Because light has a fixed speed, it creates a delay between events and awareness. Something can happen, and the universe does not immediately know about it everywhere. There is always a wait. That wait grows longer the farther away you are from the source. This delay is not a technical inconvenience. It is a fundamental feature of reality. There is no workaround, no clever engineering, no shortcut through space. Even gravity, which for a long time was thought to act instantaneously, turns out to propagate at the speed of light as well. So when we look out into space, we are not surveying the universe as it exists right now. We are sampling different moments in its past arranged by distance. Nearby objects appear relatively recent. Farther objects appear increasingly ancient. At the extreme edge of observation, we are seeing the universe as it was shortly after it began. This is why the speed of light acts like a kind of cosmic shutter. It limits how much of the universe's story has had time to reach us. The observable universe is not defined by how far light could go if the universe was static and eternal. It is defined by how far light has actually travelled in a universe that has a finite age and is constantly changing. If the universe were infinitely old, the observable universe might also be infinite. Light from arbitrarily distant regions would have had time to arrive, but the universe has not existed forever. It has a beginning, at least as far as our current understanding goes, and from that beginning, light has been travelling outward for a finite amount of time. That immediately places a limit on observation. No matter how sensitive our instruments become, we cannot see beyond the distance light has covered since the universe began. That distance is not something we can increase by waiting a little longer with better equipment. It increases only as time itself passes. This is where the phrase, speed limit of the universe, earns its weight. The speed of light is not just fast, it is the rate at which causality itself propagates. It determines which events can influence which other events. It defines what can be connected and what remains isolated. If something is happening right now in a galaxy far beyond our observable horizon, it is causally disconnected from us. There is no way for that event to affect us, and no way for us to learn about it, because the universe has not existed long enough for light or any signal to bridge that gap. This also means that the observable universe is not symmetrical in time. We see much more of the past than the present. In fact, we never see the present at all, except at our own location. Everything else is delayed by the time it takes light to travel. That delay can be small or enormous. Light from the moon takes just over a second to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest star beyond the Sun takes more than 4 years. Light from distant galaxies takes billions of years. At a certain distance, the delay becomes so large that we are no longer seeing stars or galaxies as mature structures. We are seeing the raw ingredients of the early universe, before stars had formed at all. Beyond that, we see a glowing fog of radiation, left over from when the universe was still hot and dense. And beyond that, observation stops entirely, not because the universe stops, but because light had not yet begun travelling freely. This speed limit also means that size in the universe is not just a matter of distance, it is a matter of time. When we say that something is a certain number of light years away, we are describing both how far it is and how long its light has been travelling. A light year is not a unit of time. It is a unit of distance defined by time. It is the distance light travels in 1 year. That definition bakes the speed limit directly into our language. When cosmologists talk about the size of the observable universe, they are not measuring a static sphere. They are describing the current radius of a region whose boundary is set by how far light has travelled since the beginning, taking into account the expansion of space itself. This is where intuition often falters. If the universe is 13.8 billion years old, it might seem reasonable to assume that the observable universe has a radius of 13.8 billion light years. Light travelling for 13.8 billion years should cover 13.8 billion light years. Simple enough. But the universe has not been sitting still during that time. Space itself has been expanding. While light was travelling toward us, the distance between us and its source was increasing. That means the light has been crossing a moving target, so to speak. As a result, the current distance to the most distant observable regions is much larger than the distance light would cover in a static universe. The observable universe is far bigger than 13.8 billion light-years in radius. We will unpack that carefully later, but the key point here is that the speed of light interacts with expansion in a way that stretches distances beyond naive expectations. Still, no matter how expansion complicates the picture, the speed limit remains firm. Light always moves at the same speed locally. Space can stretch, distances can grow, but no signal outruns light. This has another consequence that often goes unnoticed. There are regions of the universe that are currently observable, but will not remain observable forever. Because the expansion of the universe is accelerating, driven by a mysterious effect known as dark energy. Some distant galaxies are receding from us so quickly that light emitted from them today will never reach us. We are seeing them now only because their light began its journey long ago when they were closer. Future light from those same galaxies will be carried away by the expansion of space faster than it can travel toward us. Over unimaginably long timescales, they will fade from view, slipping beyond our observable horizon. So the observable universe is not just bounded by the past, it is also bounded by the future. The speed limit of light, combined with cosmic expansion, creates a dynamic window of visibility that opens and closes over time. From a human perspective, this is strange. We are used to thinking of vision as something that can always be improved. Better lenses, bigger mirrors, higher resolution. But no amount of technological progress can overcome the finite speed of light or the finite age of the universe. Observation is constrained not by effort, but by geometry and history. There is something quietly humbling about that. It means that the universe does not owe us full access. We learn what we can, when we can, from where we are, and no farther. Knowledge is always local, even when it reaches across billions of light years. At the same time, the speed limit of the universe gives structure to what we can know. Because light moves at a constant speed, we can use it as a ruler. By measuring how light changes as it travels, how it stretches, dims, or shifts in colour, scientists can infer distances, motions, and ages. Without a speed limit, none of that would work. If light travelled infinitely fast, there would be no delay to measure, no record of the past preserved in transit. the universe would be observationally flat, stripped of depth in time. Paradoxically, the limit that restricts us is also what allows us to reconstruct cosmic history at all. The slowness of light on cosmic scales turns the universe into an archive. Every photon that reaches us carries a timestamp. It tells us how long it has been travelling, and by extension how far it has come. By collecting enough of these timestamps from different distances, scientists can piece together a timeline of the universe's evolution. This is why the observable universe is not just large but layered. Nearby space shows recent history. Distant space shows ancient history. The speed limit creates a natural ordering. As you sit with this idea, it becomes easier to see why the observable universe is not simply everything we can see right now. It is everything that has had time to announce itself, and that announcement is ongoing. Even as you listen, light is arriving from regions that were previously beyond our horizon. The observable universe is growing, slowly but steadily as time passes. But growth does not mean unlimited access. There will always be regions beyond reach, separated not by emptiness, but by time and expansion. There is something quietly counterintuitive about the way the universe reveals itself. In everyday life, distance and time feel like separate ideas. Something can be far away without being old, and something can be old without being far away. In the cosmos, those two concepts are inseparably linked. The farther out we look, the further back in time we're seeing. Distance is not just space, it is history. This connection follows directly from the speed limit we've already eased into. Because light travels at a finite speed, every observation carries a delay. That delay is small for nearby objects and immense for distant ones, but it is always there. No matter where you point a telescope, you are never seeing the universe as it exists right now, except in your immediate surroundings. You are seeing it as it was, when the light began its journey toward you. This turns astronomy into a kind of archaeology, except instead of digging downward through layers of soil, scientists look outward through layers of time. Each increase in distance corresponds to an earlier chapter in the universe's story. Nearby stars show us relatively recent events. Distant galaxies show us conditions from billions of years ago. At the extreme edge of observation, we see the universe when it was still young, hot, and unrecognizable compared to today. It's worth slowing down with this idea, because it reshapes how we think about observation itself. When you look across a room, the delay is so tiny that it feels irrelevant. Light takes a few billionths of a second to cross that distance. Your brain treats what you see as effectively real time. Even when you look at the moon, the delay of about a second doesn't feel meaningful. The moon still appears present. But as distances grow, delays accumulate. 8 minutes to the sun, hours to the outer planets, years to nearby stars, thousands of years to distant regions of our galaxy, millions of years to nearby galaxies, billions of years to the farthest galaxies we can observe. At those scales, now loses its meaning. The universe becomes a mosaic of different eras, all visible at once, layered by distance. When astronomers say they are studying the early universe, they do not mean they are reconstructing it entirely from theory. They are observing it directly as it appeared long ago. The light arriving today from the most distant objects left them when the universe was a fraction of its current age. This is why telescopes are often described as time machines, though not in the dramatic sense of science fiction. They do not allow travel into the past. They allow observation of the past, and that distinction matters. Nothing about this violates causality or physics. It is simply a consequence of light's finite speed. A more powerful telescope does not let you see things faster. It lets you see things farther away, and therefore further back in time. When astronomers build larger mirrors or place observatories in space, they are not just improving clarity. They are extending the reach of observation into earlier cosmic eras. This also explains why the most distant galaxies look so different from nearby ones. They are not merely farther away versions of the same objects, they belong to a younger universe. Many are smaller, less organised and more chaotic. They often lack the familiar spiral shape seen in nearby galaxies, because those structures had not yet fully formed. Stars, too, tell a time-based story. The earlier stars were made almost entirely of hydrogen and helium, the simplest elements produced in the early universe. Heavier elements like carbon, oxygen and iron were forged later, inside stars and spread by explosions. When astronomers observe extremely distant stars or galaxies, they are often seeing a universe that has not yet been enriched by multiple generations of stellar life and death. This layering of time allows scientists to test theories of cosmic evolution. Instead of guessing how galaxies might have formed, they can look across distance and watch formation in progress at different stages. Nearby regions show mature structures, distant regions show earlier steps. The universe itself becomes the experiment. One of the most striking consequences of this is that there is no single age of the universe visible at once. The night sky is not a snapshot taken at a single moment. It is a collage assembled from different times. Every point of light carries its own timestamp. Even the Milky Way, which feels like home, contains time delays. Light from stars near the galactic center takes tens of thousands of years to reach us. When we look toward that dense region, we are seeing it as it was when humans were just beginning to spread across the Earth. Beyond our galaxy, the effect becomes even more pronounced. The Andromeda galaxy appears as it was about 2.5 million years ago. At that time, early humans were just beginning to use simple tools. The light arriving now began its journey long before recorded history. And yet, Andromeda feels close by cosmic standards. It is part of our local group of galaxies. When astronomers look deeper, they encounter galaxies whose light began travelling before Earth existed, before the Sun formed, before the Milky Way had settled into its current shape. At extreme distances, galaxies appear as faint reddish smudges, not because they are intrinsically red, but because the expansion of the universe has stretched their light over billions of years. That stretching, called redshift, is itself a record of time. The more stretched the light, the longer it has been travelling, and the earlier the era it represents. Redshift becomes a kind of clock. By measuring how much a galaxy's light has been stretched, scientists can estimate how long ago it was emitted. Distance, time and expansion become interwoven measurements of the same underlying process. Eventually, if we look far enough, galaxies disappear entirely. There comes a point where the universe was so young that stars had not yet formed. Before stars, there were no galaxies to shine. Instead, the universe was filled with hot gas and radiation. The farthest light we can observe does not come from stars or galaxies at all. It comes from a time about 380,000 years after the universe began, when the cosmos cooled enough for light to travel freely. Before that moment, the universe was opaque, more like a glowing fog than empty space. The light released at that time has been travelling ever since. Over billions of years it has cooled and stretched until it now arrives as faint microwave radiation. This ancient glow marks the limit of how far back we can see. Beyond it, the universe is invisible to electromagnetic observation, not because it did not exist, but because light could not escape. So the observable universe has a temporal boundary as well as a spatial one. It extends back to the moment when light first became free to travel. Anything earlier than that remains hidden from direct observation. This makes the observable universe a record not just of space, but of change. It captures the universe at different ages, revealing how complexity emerged over time. Early simplicity gives way to structure, structure gives way to diversity. Diversity gives way to the rich cosmic environment we see nearby. There is also something quietly comforting in this perspective. It means the universe carries its own memory. Events do not vanish the moment they happen. Their effects travel outward, preserved in light, crossing immense distances. The universe remembers itself, and we learn by reading those memories as they arrive. At the same time, this memory is incomplete. Not all light survives the journey. Some is absorbed, some is scattered, some is stretched beyond detectability. The past that reaches us is filtered. It is a partial record shaped by the medium it travelled through. This is why cosmology relies on patterns rather than individual events. No single observation tells the whole story. But taken together, observations from different distances and times form a coherent picture. The same physical laws appear to operate everywhere. The same relationships repeat. This consistency allows scientists to connect distant observations into a unified timeline. It also explains why surprises are so valuable. When distant objects behave differently than expected, it often means we are witnessing physics under conditions that no longer exist nearby. The early universe was denser, hotter, and more energetic. Observing it allows us to test theories at extremes that cannot be recreated on Earth. Looking far away, then, is not just about satisfying curiosity. It is how we learn where the universe came from and how it arrived at its present state. Distance becomes a tool, not an obstacle. As this idea settles in, it becomes clear that the observable universe is not just large in space. It is deep in time. Every direction you look is a journey backward, and every increase in distance is a step further into cosmic history. From here, the story naturally turns toward the question of age. If looking far away shows us earlier eras, then how old is the universe as a whole? How do scientists arrive at a number for its age? And what does that number actually mean when time itself is woven into observation? When the age of the universe is given as 13.8 billion years, it can sound like a neat, finished answer, as if someone checked a cosmic clock, wrote down the number, and moved on. In reality, that figure is the result of decades of careful measurement, cross-checking, revision, and quiet disagreement. It is not a guess, and it is not arbitrary. It is a number stitched together from light, motion, temperature, and the slow unfolding of cosmic history. To understand what 13.8 billion years really means, it helps to step away from the idea of age as something obvious. On Earth, age is often straightforward. We mark birthdays, we count years since an event. We use calendars anchored to familiar cycles. The universe does not come with a birth certificate, and there was no observer present at its beginning with a stopwatch. Everything we know about its age has been inferred indirectly, using the universe itself as evidence. The starting point is expansion. The universe is not static. Space itself is stretching, carrying galaxies away from one another. This fact, first noticed in the early 20th century, is foundational. When astronomers measure distant galaxies, they find that nearly all of them are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This relationship is not about motion through space in the usual sense. It is about space expanding between objects. Once this expansion was established, a natural question followed. If the universe is expanding now, then in the past it must have been smaller. Go far enough back, and everything would have been much closer together. Continue that reasoning, and you arrive at a state where the universe was extremely hot, dense, and compact. This idea became the basis of what is now called the Big Bang model. The Big Bang is not an explosion in space. It is an expansion of space. There was no center and no edge. Every region was once closer to every other region. The age of the universe, then, is the time that has passed since that early hot, dense state began expanding into what we observe today. But how do we put a number on that time? One method comes from measuring how fast the universe is expanding right now. If you know the current expansion rate, and you understand how that rate has changed over time, you can run the cosmic story backward mathematically. It is similar to watching a video of a balloon inflating and estimating when it was smallest based on how fast it is growing. The current expansion rate is known as the Hubble constant. Despite its name, it is not truly constant in time, but it describes how fast galaxies are receding from each other today. Measuring it precisely has turned out to be surprisingly difficult. Different methods produce slightly different results, a tension that remains an active area of research. Still, even with those uncertainties, the expansion rate provides a strong constraint on the universe's age. A faster expansion implies a younger universe. A slower expansion implies an older one. When astronomers plug in the best available measurements and account for how expansion has changed over time, they consistently arrive at an age very close to 13.8 billion years. But expansion alone is not enough. Independent lines of evidence are crucial. One of the most important comes from the oldest light we can observe, the faint microwave glow that fills all of space. This radiation is a leftover from the time when the universe first became transparent, about 380,000 years after the beginning. The detailed pattern of tiny temperature variations in this radiation encodes a wealth of information. It reflects the density, composition, and geometry of the early universe. When scientists analyze these patterns using well-tested physical laws, they can infer how long the universe has been expanding since that early moment. The age that emerges from this analysis aligns remarkably well with the age derived from expansion measurements. Another approach involves the oldest known objects in the universe. Some stars are extremely old, formed early in cosmic history. By studying their composition and evolution, scientists can estimate how long they have been shining. These stellar ages place a lower limit on the age of the universe. After all, the universe must be at least as old as its oldest stars. When astronomers examine the most ancient star clusters, they find ages of around 12 to 13 billion years. That leaves room for the universe itself to be slightly older, consistent with the 13.8 billion year figure. If the universe was significantly younger, there would not have been enough time for these stars to form and evolve as observed. What makes this convergence compelling is that these methods are independent. They rely on different physics, different observations, and different assumptions, yet they all point to the same general time frame. This agreement gives scientists confidence that they are not simply fitting data to a preconceived answer. Still, it is important to understand what this age actually refers to. When we say the universe is 13.8 billion years old, we are talking about time measured along the history of cosmic expansion. We are not saying that every part of the universe experienced time in exactly the same way. As we have already seen, time itself can flow differently under different conditions. In the early universe, conditions were extreme. Temperatures were incredibly high. Densities were enormous. Physical processes unfolded in ways that have no direct analogue today. Time as we experience it now is not a perfect guide to what those early moments were like. Nevertheless, the concept of elapsed cosmic time remains meaningful and measurable within our current theories. It is also worth noting that the age of the universe is not something we observe directly at the edge of space. When we look out to the farthest observable regions, we do not see the universe at 13.8 billion years old. We see it as it was much earlier. The oldest light we observe comes from a universe less than 500,000 years old. The age figure is reconstructed by connecting those early observations to the present through a well-tested model of cosmic evolution. It is a synthesis, not a snapshot. Another subtle point is that the universe did not begin in the form we recognize today. The first fraction of a second after the beginning is still poorly understood. Our current theories work extremely well from a tiny fraction of a second onward, but they may not describe the very earliest moment itself. When scientists quote 13.8 billion years, they are referring to the time since the universe entered a phase we can describe reliably, not necessarily the absolute beginning in a philosophical sense. This distinction matters because it keeps the age from becoming a metaphysical claim. It is a physical one, grounded in observable consequences. The universe behaves today as though it has been expanding for about 13.8 billion years. That behavior is what the age reflects. From a human perspective, 13.8 billion years is an almost meaningless number. Our brains are not built to grasp billions intuitively. We can say the words, but they do not correspond to lived experience. To make sense of it, People often compress the universe's history into a calendar year or a single day. While these analogies can be helpful, they can also create a false sense of clarity. In truth, the age of the universe is not something meant to feel intuitive. It is meant to be accurate. It is a result that emerges from consistency across many kinds of evidence. What matters for our exploration is not memorizing the number, but understanding what it enables. Knowing the universe's age allows scientists to place limits on how far light could have travelled. It sets the scale for the observable universe. It defines the maximum look-back time available to observation. Without an age, the observable universe would be undefined. With it, observation gains structure. It also provides a timeline for cosmic events. Galaxies did not appear immediately. Stars took time to form. Heavy elements took even longer. Planetary systems and eventually life required billions of years of prior cosmic evolution. The age of the universe is the stage length on which all of this unfolded. As the universe aged, its conditions changed. Expansion cooled it. Matter clumped. Structures grew. The universe became more complex. The 13.8 billion year figure is not just a count of years. It is a measure of how much transformation has already occurred. There is also something quietly grounding about knowing that the universe has a finite age. It means there was a time when the things we see did not yet exist. It means the night sky has not always looked this way. It means change is fundamental, not incidental. At the same time, the age is not a countdown. It does not tell us how much time remains. The universe is not aging toward a known endpoint in the way living organisms do. Its future is governed by expansion, energy, and conditions that are still being studied. For now, the age serves as an anchor. It connects expansion, observation, and distance into a single coherent picture. Light has been travelling for 13.8 billion years. Space has been stretching for that long. The observable universe is defined by that shared history. As this idea settles, it becomes easier to see why size in cosmology does not map cleanly onto age. If light has been travelling for 13.8 billion years, why is the observable universe larger than 13.8 billion light-years across? At first glance, the numbers seem like they should line up neatly. If the universe is about 13.8 billion years old, and if light travels 1 light-year per year by definition, then it feels reasonable to expect that the farthest light we can see must have travelled about 13.8 billion light-years. That intuition is understandable, and it's also incomplete. The observable universe turns out to be far larger than that simple calculation suggests, and the reason has everything to do with how space itself behaves. To see why, it helps to temporarily set aside the idea of space as a fixed, unmoving stage. In everyday life, distances are stable. The space between two cities does not stretch while you're driving. The space between two chairs does not grow while you're sitting in the room. Because of this, it's natural to imagine light travelling across a static backdrop, steadily closing the distance between a source and an observer. The universe does not provide that kind of backdrop. Space itself expands. This expansion is not objects moving through space away from a central point. It is the space between objects increasing everywhere at once. Galaxies are largely staying where they are locally, but the distances separating large-scale structures grow over time. This distinction is subtle, but it is the key to understanding why the observable universe is larger than its age expressed in light years. When light begins its journey toward us from a distant region, it does not travel across a fixed distance. The distance itself is changing while the light is in transit. As the universe expands, the space between the light and its destination stretches, effectively lengthening the path the light must cross. This means that light emitted billions of years ago started its journey from a region that was much closer to us than it is now. While the light was travelling, space continued to expand. carrying that region farther away. By the time the light finally arrives, the source is vastly more distant than it was when the journey began. So when we say we're observing light that has been travelling for 13.8 billion years, we're not saying that its source is currently 13.8 billion light years away. We're saying that the light has been in transit for that long, through a universe that has been stretching the entire time. This distinction is the heart of the matter. To make it more concrete, imagine walking towards someone on a moving walkway that is also slowly pulling you apart. You're walking forward at a steady pace, but the walkway is moving backward beneath your feet. You're making progress, but not as quickly as you would on solid ground. The longer the walkway runs, the more distance you have to cover. Light in the expanding universe is doing something similar. It always moves at the same speed locally, but the space it is crossing keeps changing. Over cosmic timescales, that effect becomes enormous. Because of this, the current distance to the most distant observable regions is not determined simply by how long light has been travelling. It is determined by the entire expansion history of the universe. When cosmologists calculate the size of the observable universe, they take this expansion into account. They model how fast space has been stretching at different times, how the expansion rate changed as the universe evolved, and how light propagated through that evolving geometry. The result is surprising if you are meeting it for the first time. The radius of the observable universe is not 13.8 billion light years. It is about 46 billion light years. That means the observable universe is roughly 93 billion light years across. This does not mean light travelled faster than light. It does not mean the universe broke its own speed limit. It means that while light was travelling, the universe expanded in such a way that the distance between the starting point and the end point grew dramatically. The early universe plays an especially important role here. Shortly after the universe began, expansion was extremely rapid. Space grew much faster in its early stages than it does today. During that period, light was trying to make progress through a universe that was expanding aggressively beneath it. As the universe cooled and evolved, the expansion rate slowed for a long time, then later began accelerating again due to dark energy. Each of these phases affected how far light could travel and how distances changed during its journey. So the size of the observable universe is not a simple multiplication of speed and time. It is an integral over cosmic history. It reflects how space expanded at every stage while light was on the move. Another source of confusion comes from how we use the word distance. In cosmology, there are multiple ways to define distance, depending on what you are trying to describe. There is the distance light has travelled. There is the distance to an object at the moment the light was emitted. There is the distance to that same object now, after billions of years of expansion. All of these distances are valid in their own contexts, but they are not interchangeable. When we say the observable universe has a radius of about 46 billion light years, we are talking about the current proper distance to the most distant regions whose light has reached us. That is a present-day measurement, not a travel distance. This distinction matters because it prevents a common misunderstanding. The observable universe is not a bubble expanding into empty space. It is a region defined by which parts of the universe have been able to communicate with us so far. The distances involved are measured along the fabric of space as it exists now. It also means that the observable universe can be much larger than the distance light has physically travelled. Those two quantities answer different questions. Light has been travelling for 13.8 billion years. Space has been expanding for 13.8 billion years. The combination produces a present-day observable radius far larger than either number alone would suggest. There is another subtle implication here. Some regions of the universe are currently farther than 46 billion light-years away from us. Those regions exist, assuming the universe extends beyond our horizon, but they are not observable. Their light has not reached us, and in some cases never will. The observable universe is therefore not the same as the universe at large. It is the intersection of time, expansion, and causality. This helps clarify why asking for the edge of the universe can be misleading. The 46 billion light-year distance is not a wall. It is the current location of the furthest events whose light has had time to arrive. As time passes, that boundary can change, but not in a simple outward march. Because expansion is accelerating, there are limits to how much farther our observable region can grow. Some distant regions are already receding so quickly that new light emitted from them will never overcome the expansion and reach us. The observable universe has a horizon not just in the past but in the future as well. All of this reinforces a central theme. Size in cosmology is dynamic. It depends on when you measure it, how you define distance, and how the universe has behaved over time. The reason the observable universe is bigger than 13.8 billion light-years is not an exception or a trick. It is a natural consequence of living in an expanding universe with a finite age and a finite speed for information. As these ideas settle together, the scale of the observable universe begins to feel less paradoxical. The numbers stop competing with one another and instead describe different aspects of the same story. Time tells us how long light has been travelling. Expansion tells us how distances have changed. Observation tells us which regions are connected to us by that shared history. When people first encounter the idea that the universe is expanding, the explanation they are most likely to hear involves a balloon. It's simple, visual, and approachable, which is why it shows up in classrooms, documentaries, and conversations between curious minds trying to get a foothold on something enormous. But like all analogies, it is both helpful and misleading. It illuminates certain features of cosmic expansion very clearly, while quietly distorting others. Understanding both sides is essential if the size of the observable universe is going to make real sense rather than just sounding impressive. So let's take the balloon seriously for a moment, not as a metaphor to memorize, but as a tool to examine carefully. Imagine an ordinary balloon before it's inflated. You draw small dots on its surface with a marker. Each dot represents a galaxy. At this stage, the balloon is small and the dots are close together. Now you begin to inflate the balloon. As it grows, the surface stretches and the dots move away from one another. No dot is special. No dot is at the center of the surface. From the perspective of any dot, all the other dots are receding. This captures something very important about the real universe. Galaxies are not flying away from a central explosion through empty space. Instead, space itself is expanding between them. From any galaxy, the universe appears to be expanding uniformly. The farther away another galaxy is, the faster it appears to be receding, not because it is moving faster through space, but because there is more space between them that is stretching. In that sense, the balloon analogy works well. It shows why there is no center of expansion within the universe. It shows why every observer sees themselves at the center of their own observable universe. And it shows how distances can increase everywhere at once, without requiring galaxies to be actively travelling through space like shrapnel from a blast. It also helps explain why the observable universe looks the same in all directions on large scales. Just as the surface of the balloon stretches uniformly, space expands in a way that preserves large-scale uniformity. Even those small regions can be clumpy and structured. But the moment we lean too heavily on the balloon, cracks begin to appear. The first limitation is obvious once you notice it. The balloon's surface is two-dimensional, while the universe has three spatial dimensions. The balloon analogy asks you to imagine living on the surface, not inside the balloon. That mental shift is manageable, but it already introduces abstraction that can quietly distort intuition. More importantly, the balloon expands into something. There is air outside the balloon. There is space surrounding it. In the real universe, there is no external space into which the universe expands. Expansion is not movement into an outside region. It is the stretching of space itself. This distinction matters because the question, what is the universe expanding into, is a natural one, and the balloon analogy encourages it. The correct answer is that the universe is not expanding into anything. There is no external container. The expansion is internal to space itself. Another limitation appears when we think about the speed of expansion. On the balloon, dots move apart faster as the balloon inflates more quickly. But the material of the balloon has limits. Stretch it too fast or too far and it tears. Space does not behave like rubber. It has no material tension. It can expand without resistance, governed by the equations of general relativity rather than physical elasticity. This difference becomes important when considering very large distances. On the balloon, no dot can move faster than the rubber allows. In the universe, the expansion of space can cause distant regions to recede from one another faster than the speed of light without violating any physical laws. This does not mean information is traveling faster than light. It means the space between regions is increasing. This is one of the most counterintuitive aspects of cosmic expansion, and the balloon analogy only partially captures it. On a balloon, you might imagine measuring the speed of dots as they move across the surface. In the universe, recession speed is not motion through space in the usual sense. It is a rate of increase in distance due to expansion. Another subtle issue arises when we try to connect the balloon to time. The balloon analogy often suggests a single, smooth inflation from small to large. In reality, the universe's expansion history is more complicated. The expansion rate has changed over time. Early on, the universe expanded extremely rapidly. Later, the expansion slowed as gravity dominated. More recently, expansion has begun accelerating again due to dark energy. The balloon does not naturally convey these phases, unless you carefully control how you inflate it. The analogy risks suggesting a constant expansion rate, which is not what the universe experienced. Without additional explanation, the balloon can flatten the story of cosmic expansion into something overly simple. There is also the question of scale. On the balloon, dots are all roughly the same size relative to the surface. In the universe, galaxies do not expand along with space in the same way large-scale distances do. Gravity holds galaxies, solar systems, and atoms together. The expansion of space becomes noticeable only on vast scales, between clusters of galaxies. If the balloon analogy is taken too literally, it can give the impression that everything is stretching, including objects themselves. This leads to common misconceptions, like the idea that atoms or people are expanding along with the universe. They are not. Local forces overpower cosmic expansion on small scales. The balloon analogy also struggles with the concept of horizons. On a balloon, if you draw a dot and wait long enough, you might imagine eventually being able to reach or see every other dot, given enough time and patience. In the real universe, this is not the case. Because expansion is accelerating, there are regions that are permanently beyond our reach. Light emitted from those regions now will never arrive here. The balloon analogy does not naturally include this idea of an event horizon, a boundary beyond which events cannot influence us, even given infinite time. This is where the analogy begins to fail in a deeper way. It shows expansion, but it does not show causality limits. It shows increasing distances, but not the dynamic relationship between expansion speed and the speed of light. Despite these limitations, the balloon analogy remains useful if handled carefully. It helps ground the idea that expansion is not motion through space from a center. It helps explain why the observable universe has no preferred location. And it helps clarify why distances grow even though galaxies are not actively fleeing one another. The key is to treat the analogy as a starting point, not a destination. One way to refine it is to stop thinking about the balloon as an object and start thinking about the rules governing its surface. The important part is not the rubber or the air inside. It is the relationship between points on the surface as it expands. Those relationships mirror the mathematical structure of expanding space. In that sense, the balloon is not a picture of the universe. It is a picture of the geometry of expansion. When scientists model the universe mathematically, They do not imagine balloons. They use equations that describe how distances between points change over time under the influence of energy, matter, and geometry. The balloon analogy is simply a visual aid for one aspect of those equations. This distinction helps prevent another common misunderstanding. The expansion of the universe does not mean it was once a tiny point in ordinary space. The early universe was dense and hot everywhere, not compressed into a single location surrounded by emptiness. The balloon analogy can accidentally suggest a point-like origin if one imagines the balloon fully deflated. In reality, the universe was never a point in space. Space itself was different. Smaller, denser, and hotter, but still space. Understanding these limits of the analogy becomes especially important when we talk about the size of the observable universe. The balloon can show how distances grow, but it does not tell you how far light has travelled or how expansion affects that journey. It cannot show why the observable universe is larger than its age in light years. It hints at the idea, but the details require stepping beyond the metaphor. There is also a psychological comfort in the balloon analogy that can be misleading. Balloons are familiar. They fit in your hands, they pop, they end. The universe does not behave like that. Its expansion does not imply fragility or an eventual tear in space, at least not in any straightforward sense. The balloon analogy also encourages spatial thinking where temporal thinking is required. Expansion is not just about where things are. It is about how they change over time. The observable universe is defined by that change, by how fast signals have propagated while space itself evolved. When the analogy is used carefully, with its limits clearly acknowledged, it becomes a bridge rather than a trap. It gets the mind moving in the right direction, then invites it to let go and follow the mathematics and evidence instead. This is why cosmology often returns to the balloon while simultaneously warning against taking it too literally. It opens the door, but it does not furnish the entire room. There is a moment early in the universe's history that quietly reshaped everything that came after it. It did not last long, it left no direct photograph, and yet without it, the observable universe would look radically different from the one we inhabit. This moment is known as cosmic inflation, and while the word itself can sound technical or abstract, the idea it represents is surprisingly concrete once it's approached carefully. Cosmic inflation refers to a brief period when the universe expanded at an extraordinary rate, far faster than it does today. This was not ordinary expansion stretched over billions of years. It was a sudden, dramatic growth spurt that occurred when the universe was unimaginably young, long before stars, galaxies, or even atoms existed. To understand why inflation matters, it helps to remember what the universe was like at the beginning, as far as current evidence allows us to trace it. In its earliest moments, the universe was extremely hot and dense. Energy dominated everything. Temperatures were so high that particles could not form stable structures. Space itself was compressed into a much smaller state than anything we see today. At that stage, the universe was already expanding, but expansion alone does not explain several striking features of what we observe now. These features puzzled scientists for decades and eventually led to the idea of inflation. One of those puzzles involves uniformity. When astronomers look at the universe on the larger scales, they find that it is remarkably similar in all directions. The temperature of the early universe, inferred from ancient radiation, is nearly the same everywhere, with only tiny variations. This is surprising because regions on opposite sides of the observable universe appear to have been too far apart to ever exchange information or energy under ordinary expansion. If light could not travel between those regions early on, how did they end up so similar? This question is known as the horizon problem. It suggests that distant parts of the universe somehow coordinated their properties despite being causally disconnected under standard expansion. Another puzzle involves geometry. Observations indicate that space is very close to geometrically flat on large scales. That means parallel lines behave as expected, and the angles of large triangles add up in familiar ways. Achieving this kind of flatness requires extremely precise initial conditions if the universe evolved under ordinary expansion alone. Any small deviation early on should have grown over time, leading to noticeable curvature today. This sensitivity to initial conditions is known as the flatness problem. It suggests that something acted early on to smooth out the geometry of space. There is also the issue of unwanted relics. Many theories predict that the early universe should have produced exotic particles or structures in large numbers, yet we do not observe these relics today. Something seems to have diluted them away. Cosmic inflation addresses all of these puzzles at once. According to the idea of inflation, the universe underwent a period of extremely rapid expansion very early in its history. During this brief interval, space expanded exponentially, growing by an enormous factor in a fraction of a second. Regions that were once tiny, uniform, and in close contact were stretched to vast scales. This stretching explains uniformity. Before inflation, the entire region that would later become the observable universe was small enough for all its parts to interact and reach similar conditions. Inflation then expanded that uniform region to cosmic proportions, making it appear smooth and consistent across vast distances today. It also explains flatness. Rapid expansion flattens space in much the same way that inflating a balloon makes its surface appear flatter over small regions. Any initial curvature becomes negligible when space grows large enough. Inflation naturally drives the universe toward geometric flatness, regardless of small initial deviations. As for unwanted relics, inflation dilutes them. Anything present before inflation becomes spread so thin by the expansion that its density drops to nearly zero. This helps explain why certain predicted structures are not observed today. What makes inflation especially important for our topic is how dramatically it affects the size of the observable universe. Inflation did not just add a little extra expansion, it magnified distances on a scale that ordinary expansion alone could never achieve in the same amount of time. A region of space smaller than a proton could, through inflation, grow to a size larger than entire galaxies. And this happened very early, setting the stage for everything that followed. Because of inflation, the observable universe today is vastly larger than it would be if the universe had expanded smoothly from the beginning without this growth spurt. Inflation stretched the fabric of space so thoroughly that light emitted long ago had to cross an already enormous and still growing distance to reach us. This helps explain why the observable universe is about 46 billion light-years in radius, even though the universe is only 13.8 billion years old. Inflation gave space a head start. It created a universe that was already large before ordinary expansion had much time to act. It's important to emphasize that inflation does not violate the speed limit of the universe. Nothing during inflation traveled through space faster than light in the usual sense. Instead, space itself expanded. Distances increased because the metric of space changed, not because objects were racing through it. This distinction is subtle, but essential. Inflation involves the behavior of space, not motion within space. The speed limit applies to signals and particles moving locally. It does not limit how quickly space itself can expand. This is why inflation can stretch regions apart faster than light could travel between them, without breaking any physical laws. It changes the geometry, not the traffic. Evidence for inflation is indirect but compelling. The strongest support comes from the pattern of tiny fluctuations seen in the ancient radiation filling the universe. These fluctuations match predictions made by inflationary models about how quantum scale variations would be stretched to cosmic sizes. Inflation suggests that small quantum irregularities in the early universe were amplified, becoming the seeds of later structure. Over time, gravity acted on these seeds, pulling matter together to form galaxies, clusters, and the cosmic web. In this sense, inflation connects the smallest scales imaginable with the larger structures we observe today. Quantum physics and cosmology meet in this early moment, linking the behavior of tiny fluctuations to the distribution of galaxies across billions of light years. There are different versions of inflationary theory, each proposing a slightly different mechanism or timeline. Some involve specific fields driving expansion. Others explore variations in how inflation begins or ends. What they share is the core idea that a rapid early expansion occurred and left lasting imprints on the universe. Inflation is not yet directly observed in the way stars or galaxies are observed. It is inferred from consistency. Models with inflation explain multiple features of the universe at once, using the same underlying assumptions. Without inflation, those features require fine-tuning or separate explanations. Still, inflation remains an active area of research. Scientists continue to refine models, search for additional signatures, and test predictions. Future observations may confirm specific versions or reveal new details. For our purposes, what matters most is inflation's role in shaping scale. Without inflation, the observable universe would likely be far smaller and far less uniform. The enormous distances we now describe would not exist in the same way. Inflation also changes how we think about what lies beyond the observable universe. If inflation stretched space so dramatically early on, then regions far beyond our horizon may exist that were once extremely close to us. The universe could be vastly larger than the observable region, perhaps even infinite extent. This possibility follows naturally from inflationary models. They often predict that the universe extends far beyond what we can see, with our observable universe being just one patch within a much larger whole. At the same time, inflation reinforces the idea that observation is limited. Even if the universe is enormous beyond our horizon, inflation makes it possible for those regions to be permanently inaccessible. Expansion can separate regions so thoroughly that no signal will ever cross the gap, so inflation both enlarges the universe and deepens its horizons. It makes the observable universe big while also making the total universe potentially far bigger still. There is a quiet elegance to this. The same process that smoothed the universe and seeded its structure also placed firm limits on what any observer can know. Inflation did not make the universe transparent in all directions. It made it structured and bounded in observation. As this growth spurt fades from view, ordinary expansion takes over. The universe cools, particles form, atoms assemble, light decouples from matter and begins its long journey across space. From that point on, the observable universe grows in a more familiar way, governed by the speed of light and the ongoing expansion of space. But the imprint of inflation remains. It is written into the size of the observable universe, into its uniformity, and into the pattern of structures that later emerged. Understanding inflation helps resolve the feeling that the observable universe is too big for its age. It shows that the universe's scale is not simply the product of steady growth over time. It is the result of a complex history, with periods of rapid change followed by long eras of gradual evolution. With inflation in mind, the enormous size of the observable universe becomes less mysterious and more coherent. The numbers stop feeling arbitrary and start reflecting a sequence of physical processes that unfolded step by step. Numbers have a way of slipping past the mind when they get too large, and the size of the observable universe is one of those cases where the figure can be stated correctly and still not really land. Saying that the observable universe is about 93 billion light-years across is accurate, but accuracy alone does not guarantee understanding. That number needs context, unpacking, and patience, because it describes something far removed from everyday experience, yet grounded in careful measurement. To begin making sense of it, it helps to be precise about what that number actually represents. When scientists say the observable universe is roughly 93 billion light-years across, they're talking about its diameter, not its radius. From our position, The most distant observable regions lie about 46 billion light-years away in every direction. If you could somehow draw a straight line from one edge of the observable universe to the opposite edge, passing through our location, that line would span about 93 billion light-years. This immediately raises a question that often causes confusion. How can something be 93 billion light-years across if the universe is only 13.8 billion years old? By now, the foundation for the answer should feel familiar. Light has been travelling for 13.8 billion years, but the space it travelled through expanded while the journey was underway. The distance between the source of the light and us today is much larger than it was when the light began moving. That expansion did not happen at a steady pace. Early on, especially during inflation, distances grew extremely rapidly. Later, expansion slowed. More recently, it has begun accelerating again. The present-day size of the observable universe reflects the cumulative effect of all those phases. So the 93 billion light-year figure is not a travel distance. It is a present-day measurement of separation across space as it exists now. This distinction is subtle but essential. If someone hears 93 billion light-years and imagines light racing from one end to the other, they are picturing the wrong process. No light has crossed the observable universe from edge to edge. In fact, light from opposite edges has never met. Those regions are causally disconnected from each other. The diameter describes geometry, not communication. Another way to approach the number is to consider how it was calculated. Scientists did not measure the observable universe directly with a tape measure. They inferred its size by combining several pieces of information: the age of the universe, the expansion history, and the physics governing how light travels through expanding space. Using models based on general relativity, cosmologists can calculate how far a photon emitted at a given time would be from us today, given how space expanded during its journey. When they apply this calculation to the earliest observable light, they arrive at a present-day distance of about 46 billion light-years. That calculation depends on well-tested physics and observations that independently confirm the same parameters. It is not a single fragile result. It emerges consistently from multiple lines of evidence. Still, knowing how the number is derived does not automatically make it feel meaningful. 93 billion light-years is far beyond any scale the human mind evolved to handle. Even imagining a single light-year stretches intuition. A light-year is about 9.5 trillion kilometers. Multiply that by 93 billion, and the result becomes a figure so large it stops behaving like a number and turns into an abstraction. One way people try to cope with this is by using comparisons. If you reduce the Earth to the size of a grain of sand, the observable universe would still be larger than a city. If the Milky Way were the size of a dinner plate, the observable universe would stretch far beyond the horizon. These comparisons can help momentarily, but they often collapse under their own weight. The scale difference is simply too extreme. What matters more than picturing the full span is understanding what fills it. Within that 93 billion light-year diameter are hundreds of billions of galaxies. Each galaxy contains anywhere from millions to trillions of stars. Many of those stars host planets. Many of those planets exist in environments that are still being studied. Between galaxies lie vast regions of sparse matter, shaped into filaments and voids that form the largest known structures in the universe. And yet, despite containing so much, the observable universe is mostly empty. The average density of matter is incredibly low. Galaxies are separated by enormous distances. Stars within galaxies are separated by distances that dwarf the sizes of the stars themselves. Even atoms are mostly empty space. So the size of the observable universe is not a packed container. It is an immense volume where structure exists on islands, separated by oceans of near vacuum. Another aspect of the 93 billion light-year figure that deserves attention is symmetry. The observable universe appears roughly the same size in all directions. This is not because we are at a special location, but because the universe looks statistically similar everywhere on large scales. From our perspective, we sit at the centre of a sphere 46 billion light-years in radius. From another galaxy's perspective, that galaxy sits at the centre of its own observable sphere. These spheres overlap, but they are not identical. Each observer has access to a different subset of the total universe. This reinforces an important idea. The observable universe is not an object floating in space. It is a relationship between an observer and the rest of the universe, defined by time and causality. Its size depends on when and where you ask the question. As time passes, the observable universe can change, but not in a simple way. Light from some regions that are currently observable will continue arriving. Light from other regions will never arrive, no matter how long we wait, because expansion is accelerating. So the 93 billion light-year diameter is not a promise that observation will someday include everything within that distance and beyond. It is a snapshot of what is observable now, given the universe's current age and expansion history. There is also a tendency to interpret the size of the observable universe as a statement about the size of the universe as a whole. This is not justified. The observable universe could be a small part of a much larger structure. It could also be representative of the whole if the universe is finite but larger than our horizon. Or it could be infinite in extent. Current observations cannot distinguish definitively between these possibilities. What they tell us is that the universe appears very close to geometrically flat on large scales. Flatness is consistent with both a very large finite universe and an infinite one. So when we say the observable universe is 93 billion light-years across, we're not claiming that the universe ends there. We're stating the size of the region that has been able to make itself known to us so far. Another way to think about the scale is in terms of time slices. The observable universe contains regions at many different cosmic ages. Nearby regions are seen close to their present state. Distant regions are seen as they were billions of years ago. The farthest regions are seen as they were when the universe was extremely young. All of these regions coexist in the observable universe because observation collapses space and time into a single view. The 93 billion light-year diameter is not a simultaneous picture of the universe at one moment. It is a composite assembled from different times. This helps explain why the observable universe can contain structures that formed at different stages of cosmic evolution. Some galaxies appear mature, others appear primitive. Some regions show active star formation. Others are quiet and evolved. All are visible because their light has reached us, not because they exist in the same state now. The scale also highlights how limited our perspective is. Even within 93 billion light-years, there are regions we can never interact with. Light from opposite sides of the observable universe will never cross. No signal we send will ever reach those distant edges. Causality does not span the diameter. This makes the observable universe less like a connected territory and more like a personal archive of reachable information. Despite this, the fact that the observable universe has a finite, measurable size is remarkable. It means the universe has a structure that can be described quantitatively. It means cosmology is not just storytelling, but measurement. The 93 billion light-year figure has been refined over time as measurements improved. Early estimates were less precise. As observations of expansion, cosmic background radiation, and large-scale structure became more detailed, the calculation sharpened. Today's estimate carries uncertainties, but they are relatively small compared to the magnitude of the number itself. That precision does not make the universe feel smaller. If anything, it makes its vastness more concrete. There's also an emotional component to grappling with this scale. Some people find it unsettling, others find it grounding. Knowing that the observable universe is enormous can make personal concerns feel tiny, or it can make the fact that we exist at all feel more remarkable. Neither response is right or wrong. Scale has psychological effects, and those effects vary. What matters for the story we're following is that the observable universe's size is not arbitrary. It follows logically from the universe's age, expansion, and early history. Inflation stretched space. Expansion continued. Light travelled. Distances grew. The number 93 billion light-years is the outcome of that chain of events. From here, the natural question shifts again. If the observable universe is this large, and if it is defined by what we can see, then what lies beyond it? Is there more universe past the horizon? If so, how much more, and what can we say about it without drifting into speculation untethered from evidence? Beyond the farthest light we can see, the universe does not politely stop. Nothing about the evidence suggests a wall, an edge, or a sudden absence of reality waiting just past the observable horizon. What ends there is not existence, but access. The observable horizon marks the limit of what has been able to reach us so far, not the limit of what is out there. That distinction is easy to say, and surprisingly difficult to internalize, because human intuition is deeply tied to boundaries. When we reach the edge of a map, we expect either a border or an unknown labelled space. The observable universe offers neither in a physical sense. It offers a horizon defined entirely by time, expansion, and the finite speed at which information travels. To understand what lies beyond that horizon, it helps to revisit what the horizon actually is. The observable horizon is not a place you could travel to and stand on. It is not a shell surrounding us in space. It is the current distance to the most distant events, whose light has had enough time to reach our location since the universe became transparent. That distance is about 46 billion light-years in every direction, measured in present-day terms. Beyond that distance, light has not arrived yet. In some cases, it never will, because the expansion of the universe is accelerating. So when we ask what lies beyond the observable horizon, we are really asking what exists beyond the reach of causal contact with us. The simplest answer, based on everything we know so far, is more universe. Observations show that the universe looks remarkably similar in every direction we can see. On large scales, it appears homogeneous and isotropic, meaning it has roughly the same properties everywhere and in every direction. There is no evidence of a special region, no indication that we are near an edge, and no sign that conditions change abruptly as we approach the observable limit. This uniformity is one of the strongest clues we have about what lies beyond. If the universe looks the same everywhere we can observe, it is reasonable, though not provable, to expect that it continues in much the same way beyond our horizon. That expectation is formalized in what cosmologists call the cosmological principle. It states that the universe is statistically the same everywhere on large scales. This principle is not assumed lightly. It is supported by observation. Every time scientists look farther and in more detail, they find the same general patterns repeating. Galaxies cluster in similar ways. Large-scale structures follow similar distributions. The same physical laws appear to operate everywhere light has reached us from. So when scientists speak about what lies beyond the observable universe, they are not imagining wildly different physics or alien forms of space. They are extrapolating cautiously from what is already seen. According to this view, beyond the observable horizon are more galaxies, more clusters, more voids, arranged in patterns similar to those within our reach. These regions are not special. They are simply too far away for their light to have arrived. If inflation occurred, as current evidence strongly suggests, then the universe beyond our horizon may be vastly larger than the observable portion. Inflation tends to produce universes that extend far beyond any single observer's horizon, often by an enormous factor. In many inflationary models, the observable universe is just one small patch within a much larger expanse. That expanse could be finite but extremely large, or it could be infinite in extent. At present, observations cannot distinguish conclusively between a very large finite universe and an infinite one. What they tell us is that, within the observable region, space appears very close to geometrically flat. Flat geometry is consistent with both possibilities. If the universe is finite but much larger than the observable portion, then the horizon simply marks the limit of our current view. If the universe is infinite, then there is no global edge at all, and the observable universe is an infinitesimal sample of a boundless whole. Either way, the observable horizon does not represent a boundary of existence. There is another subtle but important point. Regions beyond the observable horizon are not just unseen, they are causally disconnected from us, meaning no signal from them has influenced our region, and no signal from us has influenced them, at least not yet. This causal disconnection has real consequences. Events happening beyond the horizon cannot affect us now. They cannot shape our local environment. From a physical standpoint, they are irrelevant to our immediate future, even if they exist. This can make the question of what lies beyond feel philosophical rather than scientific. If we can never observe or interact with those regions, does it matter what is there? From a strict experimental standpoint, science deals only with what can, in principle, be observed. But cosmology also seeks coherent models that explain why the observable universe looks the way it does. Those models often make statements about regions beyond the horizon as a consequence of their internal consistency. So while we cannot directly observe what lies beyond, we can make reasoned inferences based on well-tested theories. Another concept that often enters the discussion here is the idea of multiple horizons. The observable horizon is not the only limit in cosmology. There is also what is called the particle horizon, which marks the maximum distance from which particles could have travelled to us since the beginning. Closely related is the event horizon, which marks the boundary beyond which events will never be able to influence us, even in the infinite future. Because the universe's expansion is accelerating, the event horizon is particularly important. It means there are regions that are observable now, whose light has already reached us, but whose future light will never arrive. Over time, those regions will fade from view. So the set of things we can see now is not the same as the set of things we will ever be able to see. This adds a strange temporal twist to the observable universe. Some parts of it are temporary visitors in our sky. Others are permanent. The horizon is not static. It evolves. Beyond the event horizon lie regions that are permanently inaccessible. Even if the universe continues forever, no signal from those regions will ever reach us. They are separated from us not by distance alone, but by the dynamics of expansion. This means that what lies beyond the observable horizon depends on which horizon you are considering. Beyond the particle horizon lie regions whose light has not yet arrived. Beyond the event horizon lie regions whose light will never arrive. In both cases, the expectation remains the same. There is no evidence that those regions are fundamentally different. They are simply out of reach. There is also a temptation to imagine the observable horizon as something like a shell moving outward, revealing more universe as time passes. While this is partly true, it can be misleading. Because expansion is accelerating, the observable universe will not eventually include everything that exists. The horizon will not sweep across the entire universe given enough time. Some regions will always remain beyond reach. So the observable universe is not a growing bubble that will one day encompass the whole. It is a limited window defined by cosmic history. This limitation is not a failure of technology or imagination. It is a consequence of the universe's structure. From a human perspective, this can feel unsatisfying. There is a deep desire to know what lies beyond every boundary. The observable horizon resists that desire. It is a boundary enforced by physics, not ignorance. At the same time, the fact that the observable universe has a horizon makes it scientifically meaningful. If everything were observable, cosmology would lose its structure. The presence of horizons allows precise statements to be made about causality, evolution, and scale. Another idea sometimes raised in discussions about what lies beyond is the possibility of different physical conditions. Could regions beyond the horizon have different physical constants, different laws, or different outcomes of early cosmic processes? Some speculative theories allow for this, particularly in versions of inflation that suggest different regions could settle into different physical states. In those scenarios, the observable universe would be just one domain among many, each with its own properties. These ideas are often grouped under the term multiverse, though that word covers a wide range of very different proposals. It is important to approach this topic carefully. While such ideas arise naturally in some theoretical frameworks, they remain speculative. There is currently no direct observational evidence that regions beyond our horizon have different physical laws. What we can say with confidence is that within the observable universe, the laws of physics appear consistent everywhere. That consistency supports extrapolating similar behavior beyond the horizon, at least as a working assumption. The observable horizon also has a psychological effect that is easy to overlook. It places our location in context. We're not at the centre of the universe in any absolute sense. We are simply at the centre of our own observable region, as every observer is. Someone in a galaxy beyond our horizon would have their own observable universe centred on their location, overlapping with ours in some regions and extending beyond it in others. There is no privileged vantage point. This symmetry is one of the most profound features of modern cosmology. It removes the need for special positions or directions. The universe does not organise itself around us. Observation organises itself around the observer. So what lies beyond the observable horizon is not mystery piled on mystery. It is most likely more of the same, more space, more matter, more history unfolding beyond our reach. That does not make the question meaningless. It clarifies its scope. Science can describe the observable universe in great detail. Beyond that, it can make cautious inferences based on consistency and theory. What it cannot do is provide direct images or measurements of regions that are causally disconnected. This is not a failure. It is a boundary condition. How many galaxies are there within this vast region? How are they arranged? And what does their distribution tell us about the scale we're trying to understand? Instead of beginning with numbers, it helps to begin with organization. The observable universe is not a smooth fog of matter spread evenly in all directions. It has structure, and that structure exists across many different scales, from stars bound together in galaxies, to galaxies bound together in clusters, to clusters arranged along immense filaments separated by vast empty regions. Understanding how these structures fit together is essential for grasping what the size of the observable universe actually contains. At the smallest scale relevant to this discussion are stars. Stars are the fundamental luminous building blocks of the visible universe. They form when clouds of gas collapse under gravity, ignite nuclear fusion, and shine for millions or billions of years. Our Sun is one example among hundreds of billions in the Milky Way alone. But stars rarely exist in isolation. Gravity draws them into families, and those families are galaxies. Galaxies come in a range of sizes and shapes. Some are small, containing only a few million stars. Others are enormous, containing trillions. Spiral galaxies like the Milky Way have rotating disks with arms where new stars are actively forming. Elliptical galaxies are more rounded and often contain older stellar populations. Irregular galaxies lack a clear shape, often because of interactions or mergers with others. Within the observable universe, there are an estimated hundreds of billions of galaxies. The exact number depends on how deep observations go and how faint a galaxy must be to count. As telescopes improve, the count tends to rise, because faint and distant galaxies that were once invisible become detectable. What matters more than the exact number is their distribution. Galaxies are not scattered randomly like dust. They follow patterns shaped by gravity and the initial conditions of the early universe. Galaxies tend to cluster together, forming groups and clusters bound by mutual gravitational attraction. Our own Milky Way is part of a small collection called the Local Group, which includes dozens of galaxies, the largest of which are the Milky Way and the Andromeda Galaxy. This group is itself part of a larger structure called the Local Supercluster, which stretches across hundreds of millions of light-years. On even larger scales, galaxies and clusters trace out enormous filaments, forming what is known as the cosmic web. These filaments can extend for hundreds of millions, even billions, of light-years. Between them lie vast voids, regions with very few galaxies where matter is sparse. This web-like structure did not appear randomly. It emerged from tiny variations in density present in the early universe. Inflation stretched those variations to large scales. Over time, gravity amplified them, pulling matter into denser regions and leaving emptier regions behind. What is striking about this structure is how it repeats across scale. Small clumps of stars form galaxies. Galaxies form groups. Groups form clusters. Clusters connect into filaments. Filaments outline immense voids. Each level follows similar physical rules, but the scale changes dramatically. To appreciate how this fits into the size of the observable universe, it helps to compare these structures to the overall volume. The Milky Way is about 100,000 light-years across. That is enormous on a human scale, but it is tiny compared to the observable universe, which is about 93 billion light-years across. You could fit nearly 1 million Milky Ways end to end across that diameter, and that comparison still understates the difference, because galaxies are separated by large distances. The average distance between large galaxies is measured in millions of light-years. Between clusters, the distances grow to tens or hundreds of millions of light-years. And between the largest filaments, voids can span hundreds of millions of light-years, with relatively little matter inside. Despite this emptiness, the total mass contained within the observable universe is immense. Most of it is not in stars or galaxies at all, but in dark matter and dark energy. Ordinary matter, the kind that makes up stars, planets, and people, accounts for only a small fraction of the total cosmic budget. Dark matter plays a crucial role in structure formation. It does not emit light, but it exerts gravity. In the early universe, dark matter began clumping before ordinary matter could. Those clumps acted as gravitational wells, pulling gas inward and allowing galaxies to form. Without dark matter, the structures we observe today would not exist in the same way. Dark energy, on the other hand, affects structure on the larger scales by influencing expansion. It does not clump, it acts uniformly, accelerating the expansion of space and limiting how large structures can grow over time. Together, these components shape the architecture of the observable universe. One way to think about scale is to imagine zooming out steadily. At first, you see individual stars. Zoom out further, and stars blur into galaxies. Zoom out again, and galaxies become points within clusters. Continue zooming, and clusters arrange themselves into filaments and walls. Eventually, even these structures blend into a statistical pattern rather than distinct objects. At the larger scales we can observe, the universe appears smooth. Individual structures disappear into averages. This smoothness is not because structure vanishes, but because the scale is so large that variations become small relative to the whole. This transition from clumpiness to smoothness is important. It tells scientists that the observable universe has a characteristic scale beyond which no new structure appears. Beyond a certain size, roughly a few 100 million light-years, the universe looks statistically uniform. That uniformity allows cosmologists to define global properties like density, expansion rate, and geometry. Without it, the concept of a well-defined observable universe would be much harder to sustain. Another aspect of structure worth noting is time. The distribution of galaxies we observe today did not always exist in this form. Early in the universe's history, matter was much more evenly distributed. Structures grew gradually over billions of years. When we look far away, we see earlier stages of this growth. Distant galaxies often appear smaller, more irregular, and more actively forming stars. Large clusters are rarer in the distant universe because they had not yet had time to assemble. This means the observable universe contains structures at many stages of development, depending on how far away they are. Nearby regions show mature structures. Distant regions show younger ones. All coexist in the observable universe because observation mixes space and time. This scale of structure also highlights a limitation. While the observable universe contains enormous complexity, it does not contain everything that exists. There may be structures beyond our horizon that are larger or rarer than anything we can observe. We cannot know directly. However, the structures we do see already stretch imagination. Some filaments span distances comparable to a significant fraction of the observable universe's radius. Some voids are so large that light takes hundreds of millions of years to cross them. Yet even these immense structures are small compared to the full scale of the observable universe. They are features within it, not boundaries of it. Understanding galaxies and large-scale structure helps anchor the abstract number of 93 billion light-years to something tangible. That vast diameter is not empty. It is populated, patterned, and shaped by gravity and expansion, acting over billions of years. At the same time, recognizing how sparse matter is helps prevent misinterpretation. The observable universe is not crowded. It is mostly space, punctuated by islands of matter connected by faint threads. This balance between vast emptiness and intricate structure is one of the defining features of cosmic scale. It shows that size alone does not determine complexity. The universe manages to be both immense and delicately organized. Long before the idea of galaxies clustering along invisible threads entered scientific language, the universe was often imagined as either evenly filled or randomly scattered. Neither picture survived careful observation. What emerged instead was something far more intricate, a pattern so large that no single object defines it, yet so consistent that it appears everywhere we look on the biggest scales. This pattern is known as the cosmic web, and it represents the largest known organization of matter in the observable universe. To approach the cosmic web properly, it helps to reset expectations. This is not a structure you could ever see from a single vantage point. No telescope image shows it all at once. It reveals itself only through accumulation, through surveys that map millions of galaxies across vast regions of space and then stitch those maps together. Only when distances become immense and individual galaxies blur into statistical points does the web become visible. At its core, the cosmic web consists of filaments, nodes, sheets, and voids. Galaxies are not sprinkled evenly throughout space. They congregate along elongated filaments of dark matter and gas. Where filaments intersect, dense nodes form, often hosting massive galaxy clusters. Between these filaments lie vast voids, enormous regions with relatively few galaxies, sometimes spanning hundreds of millions of light-years. This pattern is not decorative. It is the natural outcome of gravity acting over billions of years on the earliest density variations left behind after inflation. Those tiny irregularities, amplified gradually, determined where matter would accumulate and where it would thin out. The cosmic web did not appear fully formed. Early in the universe's history, matter was distributed much more smoothly. Small fluctuations existed, but they were subtle. Over time, gravity pulled matter into denser regions. Those regions grew denser still, attracting even more matter. Less dense regions lost material and became emptier. This process is hierarchical. Small structures form first. Larger structures emerge later through mergers and accretion. Filaments thicken. Nodes grow heavier. Voids expand as matter drains away from them. What makes the cosmic web especially important for understanding scale is that it extends across the observable universe. Filaments can stretch for hundreds of millions of light-years, Chains of connected filaments can span distances approaching a significant fraction of the observable universe's diameter. Yet even these enormous features are still embedded within a much larger whole. The web is not uniform in detail, but it is statistically consistent. No matter which direction astronomers survey, the same basic pattern appears. This consistency reinforces the idea that the observable universe is representative of a much larger structure, even if that larger structure remains unseen. Dark matter plays a central role here. The cosmic web is primarily a dark matter structure. Ordinary matter, the kind that forms stars and galaxies, follows the gravitational scaffolding laid down by dark matter. Gas falls into dark matter filaments. Galaxies form where gas accumulates. Light traces the web, but it does not define it. Simulations of the universe that include dark matter and known physical laws reproduce the cosmic web with remarkable accuracy. Starting from conditions inferred from early universe observations, these simulations evolve matter forward in time and naturally produce filaments, clusters, and voids that closely resemble what astronomers observe. This agreement is not trivial. It suggests that the same physical principles apply across scales spanning many orders of magnitude. The largest structures in the universe emerge from the same gravity that governs falling apples, operating patiently over vast distances and long times. Another important aspect of the cosmic web is its scale dependence. On small scales, the universe is clumpy. Stars form galaxies. Galaxies form groups. On intermediate scales, clusters and superclusters appear. On very large scales, those structures blend into the web. Beyond a certain scale, the universe becomes statistically smooth. That transition is crucial. It allows scientists to define average properties of the universe without being overwhelmed by local irregularities. The cosmic web provides texture without breaking uniformity. Understanding the web also clarifies why the observable universe looks the way it does. If matter were distributed randomly, observations would be chaotic and difficult to interpret. The web imposes order. It creates predictable correlations between where galaxies appear and how they move. Those motions carry information too. Galaxies do not merely sit in the web. They flow along filaments toward dense nodes under the influence of gravity. By measuring galaxy velocities, astronomers can infer the underlying mass distribution, including dark matter. This dynamic aspect of the web adds another layer to scale. Structures are not frozen. They evolve. Filaments feed clusters. Clusters merge. Voids expand. The cosmic web is a living pattern, changing slowly over billions of years. Time again enters the picture when distance is considered. When we observe nearby filaments, we see them in a relatively mature state. When we observe distant filaments, we see them as they were earlier, less developed, less pronounced. The web itself has a history. In the early universe, filaments were thinner and less distinct. Over time, they sharpened as matter continued to flow into them. Voids grew larger and emptier. The contrast between dense and sparse regions increased. This means the observable universe contains multiple versions of the cosmic web at different stages of evolution, depending on distance. The web we see nearby is older than the web we see far away. Both coexist in observation. The sheer scale of the web also helps anchor the idea of 93 billion light-years. Individual filaments may span hundreds of millions of light-years, but they are still small compared to the observable universe as a whole. You could fit hundreds of the largest known filaments end to end across the observable diameter with room to spare. This perspective prevents a common mistake. Seeing the largest known structures sometimes leads to the assumption that they define the universe's limits. They do not. They are features within it, not edges of it. The cosmic web also reinforces the idea that emptiness is not absence. Voids are not holes punched out of the universe. They are regions where matter density is low, not zero. Even the emptiest voids contain dark matter, gas, radiation, and the background expansion of space itself. Voids matter because they shape the flow of matter around them. They push matter toward filaments as they expand. Their presence influences the geometry of the web as much as the dense regions do. There is a temptation to imagine the cosmic web as a static lattice, but that image misses the ongoing nature of cosmic evolution. The web is not a rigid framework. It is the outcome of competing influences. Gravity pulls matter together. Expansion stretches space apart. Dark energy accelerates that stretching on the larger scales. As expansion accelerates, the growth of structure slows. Filaments will not thicken indefinitely. Clusters will stop merging once expansion dominates gravity at large scales. Over extremely long times, the web may become more isolated, with structures drifting apart faster than gravity can connect them. This future evolution adds another layer of scale awareness. The observable universe we see today represents a particular era, one in which large-scale structure is prominent and still evolving. Earlier, the web was faint. Later, it may fragment into isolated islands of matter separated by expanding space. Even now, the web is not evenly accessible. Some filaments extend beyond our observable horizon. We see only the portions whose light has reached us. The web continues beyond the horizon, presumably following similar patterns, but inaccessible to direct observation. This reinforces a recurring theme. The observable universe shows us patterns, not completeness. We see enough to understand the rules, but not enough to see the entire board. The cosmic web also has an interpretive role. It helps explain why the observable universe has a characteristic size. The web forms within the causal limits set by expansion and the speed of light. Structures larger than a certain scale cannot form because information and gravitational influence cannot travel fast enough to coordinate them. In this sense, the observable universe is not just a passive container for structure. Its size actively shapes what kinds of structure can exist within it. As the picture settles, it becomes easier to appreciate how scale operates in layers. Stars belong to galaxies. Galaxies belong to clusters. Clusters belong to filaments. Filaments trace the cosmic web. The web fills the observable universe. And the observable universe itself may be only a part of something larger. Each layer obeys the same fundamental laws, but expresses them differently depending on scale. This layered organization is not obvious when numbers are stated alone. It emerges only when size, structure, and evolution are considered together. The cosmic web is the bridge between abstract measurements and physical reality. With the largest patterns now in view, another question naturally follows. If the observable universe contains such immense structures, and if those structures are arranged without a preferred direction or center, then where are we located within all of this? Standing where we do, it is almost impossible not to feel central. Every direction we look, the observable universe stretches outward for tens of billions of light years. Distant galaxies recede away from us in all directions. The cosmic background looks nearly the same no matter where we point our instruments. From our vantage point, it truly appears as though we occupy the middle of everything that can be seen. And yet, this impression is one of perspective, not privilege. The feeling of being at the center arises naturally from how observation works in an expanding universe. Wherever you are, light reaches you from all directions at the same finite speed. That automatically places you at the center of a sphere defined by how far light has traveled since the universe became transparent. This sphere is the observable universe, and its geometry guarantees that every observer, no matter where they are, will see themselves at its center. This does not mean we occupy a special location in space. It means observation is local. To understand why this distinction matters, it helps to imagine another observer far away, in a galaxy billions of light years from us. That observer also sees galaxies receding in all directions. They also measure a nearly uniform cosmic background. They also calculate an observable universe with themselves at the center. Their observable universe overlaps with ours in many regions, but it also includes regions we cannot see and excludes some we can. Neither observer is wrong. Both are correct within their own frames of reference. This symmetry is one of the most profound lessons of modern cosmology. There is no absolute centre of the universe in space. There is no preferred location from which the universe unfolds. The laws of physics appear the same everywhere we can observe, and there is no evidence that this changes beyond our horizon. The idea that Earth or humanity occupies a central position has a long history. For much of human existence, it was natural to assume that we stood at the centre of creation. The sun appeared to circle the Earth. The stars seemed fixed to a celestial sphere rotating around us. That worldview was not foolish. It was based on everyday observation. As measurements improved, those assumptions were challenged and eventually overturned. Earth was found to orbit the Sun. The Sun was found to be one star among many in the Milky Way. The Milky Way was found to be one galaxy among countless others. Each step displaced us from a perceived centre. Modern cosmology completes that process. Not only are we not at the centre of the galaxy or the universe, the very concept of a central location loses meaning on cosmic scales. Expansion does not radiate outward from a point. It occurs everywhere. Space stretches between all distant regions simultaneously. From any galaxy, all other distant galaxies appear to recede. There is no unique origin of expansion within space itself. This is often difficult to reconcile with intuition because explosions in everyday life have centres. Fireworks burst outward from a point. Shockwaves propagate from a source. The Big Bang is often misimagined as this kind of event. In reality, it was not an explosion in space, but an expansion of space. Because of this, asking where the Big Bang happened in space is like asking where the centre of a two-dimensional surface is located from within the surface itself. The question assumes a framework that does not apply. The reason it feels as though we are at the centre of the observable universe is that the observable universe is defined relative to us. It is not an object sitting out there with a fixed position. It is the set of all events whose light has reached us. Change the observer, and the observable universe changes accordingly. This perspective can feel unsettling at first. It removes the comfort of a global frame of reference. There is no cosmic coordinate system with a marked origin. There is only local observation connected by shared physical laws. At the same time, this realization is deeply unifying. It means no observer is special. Every observer, anywhere in the universe, has access to a similarly structured observable region. The universe does not single anyone out. The uniformity of the cosmic background reinforces this idea. When astronomers measure the faint radiation left over from the early universe, they find it is almost identical in every direction. There are tiny variations, but no large-scale gradient pointing toward a centre or edge. If we were near a special location, we would expect to see asymmetries. One direction might look different from another. Expansion might behave differently depending on where we look. None of this is observed. Instead, the universe looks statistically the same everywhere, at least within the observable region. This isotropy supports the idea that our location is typical, not exceptional. There is also an important distinction between being at the centre of observation and being at the centre of mass or geometry. In a universe that is homogeneous on large scales, concepts like a centre of mass lose their usual meaning. There is no single point that everything revolves around. Mass is distributed evenly when averaged over sufficiently large volumes. Geometry behaves similarly. Space can be flat, curved, or open without requiring a central point. In a flat or infinite universe, a centre does not exist. In a finite but unbounded universe, like the surface of a sphere extended to higher dimensions, a centre exists mathematically outside the space itself, not within it. From within such a space, no location is distinguished as central. So when we say it feels like we are at the centre, what we are really saying is that observation organises itself symmetrically around the observer. This is not a statement about the universe's structure. It is a statement about how information reaches us. This distinction becomes clearer when we consider how redshift works. Galaxies farther away appear to be receding faster in all directions. This can look like expansion radiating outward from us. In reality, it is a consequence of uniform expansion. Any observer would measure the same pattern. If we were to relocate instantly to another galaxy, we would see the same behavior centered on that new location. The universe does not care where you stand. Expansion looks the same everywhere. This idea also resolves a common confusion. People sometimes ask whether we're moving through space away from some central point. On cosmic scales, we are largely at rest with respect to the expansion. We're carried along with the stretching of space itself. Our local motions are small compared to cosmic expansion. The feeling of centrality also interacts with the idea of the observable horizon. Because the horizon is centered on the observer, it creates a natural visual boundary. Everything we can see lies within a sphere centered on us. This can reinforce the illusion that we occupy a privileged position. But that boundary is not fixed in space. It is defined by time. If another observer were to calculate their horizon, it would be centered on them, not on us. This leads to a subtle but important realization. The observable universe is not a feature of the universe alone. It is a feature of the universe plus an observer. There is also a psychological component here. Human perception is inherently egocentric. We experience the world from a single point of view. Our brains are wired to treat our location as the reference point. That instinct carries over into cosmic thinking, unless it is carefully examined. Cosmology challenges that instinct by showing that the same view emerges from any location. What feels like centrality is actually universality. Even the phrase, "our observable universe," can be misleading if taken too literally. It does not belong to us in an exclusive sense. It is simply the observable universe relative to our location and time. This realization has implications for how we interpret large-scale data. When scientists model the universe, they do not assume our position is special. They assume it is typical. This assumption is not philosophical. It is testable. If our location were unusual, observations would reflect that. So far, they do not. This does not mean the universe is boring or featureless. Local variations exist. Clusters, voids, and filaments create complexity. But on sufficiently large scales, those variations average out. Being at no special location also means the laws of physics discovered here are likely universal. The same processes that govern stars, galaxies, and expansion locally should apply everywhere light has reached us from. This universality is one of the reasons cosmology can make confident statements about regions far away. It relies on the assumption, supported by observation, that physics does not change abruptly across space. The sense of not being central can feel deflating, but it can also be grounding. It places us within the universe rather than above it. We are participants in cosmic evolution, not spectators standing outside. At the same time, the fact that the observable universe centers itself around each observer gives every location a kind of equal significance. No matter where you are, the universe unfolds around you in the same fundamental way. This balance between humility and inclusion is one of the quiet philosophical consequences of modern cosmology. We are not at the center of the universe, but the universe presents itself to each observer as though they were. As we continue, this perspective naturally raises another question. If there is no center and no edge in the usual sense, does the universe have a boundary at all? Is the observable horizon merely a limit of vision, or does it hint at something deeper about the universe's shape and extent? Edges are familiar. Rooms have walls, maps have borders. Even abstract systems often come with limits that can be pointed to and named. Because of that, it feels natural to ask whether the universe has an edge, a place where space simply stops. Once the observable universe has been described as finite in size, the question almost asks itself, if there is a boundary to what we can see, is there also a boundary to what exists? To approach this carefully, it helps to separate two very different ideas that are often tangled together. One is the edge of observation. The other is an edge of space itself. They are not the same thing, and confusing them leads to many of the misconceptions surrounding cosmic size. The observable horizon, as we have already explored, is a limit imposed by time and the speed of light. It marks how far information has been able to reach us since the universe became transparent. That horizon is not a physical surface. It does not block travel. It does not reflect light. It is simply the current boundary of causal contact. An edge of the universe, by contrast, would be a physical or geometrical boundary. It would be a place where space ends, where going farther is not defined, or where the rules of geometry change abruptly. Nothing in current observations requires such an edge to exist. In fact, everything we can measure points in the opposite direction. On the larger scales we can observe, space appears smooth and consistent. The same kinds of structures repeat. The same physical laws apply. There is no sign of approaching a boundary where conditions shift or behavior changes. The universe does not appear to be thinning out or curling inward near the observable horizon. It simply continues, as far as evidence allows us to see. This is one of the reasons cosmologists are cautious about using the word edge at all. It carries implications that do not match the physics. To understand why an edge is not required, it helps to consider geometry rather than intuition. In everyday experience, space feels flat and infinite. You can walk in a straight line indefinitely without encountering a boundary, at least in principle. But other geometries are possible. A classic example is the surface of a sphere. From the perspective of someone living on that surface, there is no edge. You can travel in any direction without ever encountering a boundary, yet the surface has a finite area. It is limited but unbounded. The universe could behave in a similar way, though in higher dimensions. Space could be finite in volume but without edges, wrapping around in a way that does not require a boundary. In such a universe, travelling far enough in one direction could, in principle, bring you back to your starting point, though the distances involved might be far larger than the observable universe. This idea is difficult to visualize because it does not match everyday experience, but it is mathematically consistent and compatible with known physics. Alternatively, space could be infinite. In that case, there is no edge because there is no end. Space simply extends without bound in all directions. The observable universe would then be a finite region within an infinite whole, defined by what we can see rather than what exists. Current observations cannot definitively distinguish between these possibilities. Measurements of cosmic geometry suggest that space is very close to flat. Flat geometry is consistent with both an infinite universe and a finite but extremely large one whose curvature is too subtle to detect within the observable region. What is important here is that neither option requires an edge. The absence of an edge is also supported by how expansion works. The universe does not expand into something else. There is no surrounding space waiting to be filled. Expansion is the stretching of space itself. Asking where the edge of expanding space is assumes there is an outside reference frame, which the universe does not provide. This is why questions like what is the universe expanding into do not have meaningful answers within current physics. Expansion does not require an external container. Space does not need somewhere to go. It simply changes its internal geometry over time. An edge would imply an outside. Current models do not include one. There is another subtle point that often goes unnoticed. Even if the universe were finite, and even if it had some kind of global boundary, that boundary would not necessarily be observable or reachable. Depending on the geometry and expansion, it could be permanently hidden beyond horizons. So even in speculative scenarios where an edge exists, it would not behave like a wall you could approach or see. It would not be part of the observable universe in any straightforward way. This brings us back to the observable horizon. The horizon can feel like an edge because it is a limit of access. But access limits are not existence limits. They tell us where our information stops, not where reality stops. To make this distinction clearer, consider the horizon on Earth. Standing on a flat plane, the horizon marks the limit of what you can see. Beyond it lies more land, more ocean, more features that are temporarily hidden by curvature and perspective. The horizon feels like an edge, but it is not. The cosmic horizon functions similarly, though the mechanism is different. Instead of curvature of the Earth blocking sight, it is time and expansion limiting information. The analogy is imperfect, but the lesson carries over. A horizon does not imply an edge. There is also a historical reason why the idea of an edge persists. Early cosmological models sometimes pictured the universe as a finite sphere expanding into empty space. Were replaced with models that do not require an edge. Modern cosmology is comfortable with the idea that the universe may not have a boundary in the traditional sense. This comfort comes from consistency. The mathematics works, the observations align. There is no need to introduce an edge to explain what we see. That said, there are speculative ideas that explore boundaries or transitions. Some theories propose that our universe could be embedded within a larger structure, or that space could have different phases beyond certain regions. These ideas remain highly theoretical and lack direct observational support. They are interesting to consider, but they do not arise from necessity. What science currently supports is simpler. The universe, as far as we can observe, does not show signs of an edge. It behaves as though it extends beyond our horizon, in much the same way it exists within it. This does not make the universe boring or uniform in every detail. Local variations abound, structures form, evolution continues. But on the question of edges, the evidence points toward continuity rather than termination. Another reason edges feel intuitive is because size has been quantified. Once we say the observable universe is about 93 billion light-years across, it can sound like a container with dimensions. Containers usually have walls, but this number describes reach, not enclosure. The observable universe is not a box. It is a sphere of access centered on an observer, defined by light travel time and expansion history. Change the observer, and the sphere changes. Edges belong to objects. The observable universe is not an object. It is a relationship. This realization reframes the question entirely. Instead of asking where the universe ends, it becomes more accurate to ask how far observation extends, and how that extension changes over time. As time passes, the observable horizon can grow in some directions, and effectively shrink in others due to accelerating expansion. Regions that are observable now may not remain observable forever. Regions that are currently beyond reach may never become observable at all. This dynamic behavior is very different from the behavior of an edge. An edge is fixed, a horizon is not. There is also an emotional component to the idea of an edge. Edges offer closure. They make systems feel complete. The universe without an edge can feel unsettling because it resists completion. It offers no final boundary to rest against. But cosmology does not promise comfort. It describes what is consistent with evidence. In that sense, the absence of an edge is not a philosophical statement. It is a practical one. Introducing an edge where none is required complicates models without improving explanations. If future observations were to reveal signs of a boundary, cosmology would adapt. Science is not committed to edgeless universes as a matter of belief. It is committed to following evidence. So far, that evidence points away from edges. The question of whether the universe is finite or infinite remains open. But finite does not mean edged, and infinite does not mean unstructured. Both possibilities fit within current understanding. As this idea settles, it becomes easier to let go of the need for a final border. The universe does not have to end in order to be comprehensible. Its structure, history, and behavior already provide enough to study. With edges set aside, attention naturally turns to a related question. If the universe does not end at the observable horizon, and if it may extend far beyond it, then is the total universe finite or infinite in extent? Whether the universe is finite or infinite is one of those questions that sounds deceptively simple and turns out to be anything but. The words themselves are familiar, used casually in everyday conversation, yet when applied to the universe as a whole, they stretch beyond ordinary meaning. What makes the question especially subtle is that it does not arise from curiosity alone. It emerges naturally once size, horizons, and geometry are taken seriously. To approach this without drifting into abstraction, it helps to anchor the discussion in what science can actually test. Cosmology does not ask whether infinity feels reasonable or whether finiteness feels comforting. It asks what kinds of universes are consistent with observation and with the laws of physics as we understand them. At present, both finite and infinite universes remain viable possibilities. The key reason this question is difficult to answer lies in the limits of observation. Everything we know directly about the universe comes from within the observable region, a sphere roughly 93 billion light-years across. Beyond that region, we have no direct access. Any claim about the total size of the universe must therefore rely on extrapolation, not measurement. This does not mean such claims are arbitrary. Extrapolation in cosmology is guided by patterns, consistency, and theory. But it does mean there is a boundary between what can be tested and what must remain provisional. One of the most important clues comes from geometry. The universe can have different global geometries depending on its total energy content. These geometries affect whether the universe is finite or infinite. If space has positive curvature, similar in spirit to the surface of a sphere extended into 3 dimensions, then the universe would be finite in volume, but without edges. You could travel indefinitely without encountering a boundary, eventually returning to your starting point. In such a universe, infinity is not required to explain extension. If space has 0 curvature, often described as flat, then the universe could be infinite, extending endlessly in all directions. Flat geometry does not force infinity, but it allows it naturally. If space has negative curvature, more like a saddle shape, then the universe would also be infinite, with distances expanding faster than in flat space. Measurements of cosmic geometry indicate that space is very close to flat. The uncertainty is small, but not 0. Within that uncertainty, both a very large finite universe and an infinite universe are consistent with observations. This is an important point. Flatness does not automatically mean infinity. A universe can be finite and flat if it has certain topological properties, such as wrapping around itself in complex ways. These possibilities are mathematically consistent, though difficult to test observationally. So when cosmologists say the universe appears flat, they are not declaring it infinite. They are stating that within the observable region, geometry behaves as though curvature is extremely small. Another clue comes from inflation. Many inflationary models naturally produce universes that are much larger than the observable region. In some cases, they produce universes that are effectively infinite. During inflation, space expanded so rapidly that any initial curvature was smoothed out. Regions that were once small were stretched to enormous sizes. If inflation lasted long enough, the resulting universe would be vastly larger than what we can observe, regardless of whether it is finite or infinite in principle. This means inflation weakens the connection between observable size and total size. Even if the universe is finite, inflation could have made it so large that we will never observe any sign of its finiteness. In practical terms, a universe that is finite but trillions of times larger than the observable region behaves observationally like an infinite universe. There would be no detectable repetition, no curvature effects, and no edges within reach. So the distinction between finite and infinite becomes less about what exists and more about what can ever be known. There's also a tendency to assume that infinity would imply repetition. If the universe were infinite and uniform, then every possible configuration of matter might repeat somewhere. There could be regions identical to ours, copies of galaxies, stars, or even entire observable universes. This idea appears frequently in popular discussions, but it rests on assumptions that go beyond what is established. Infinity alone does not guarantee repetition unless additional conditions are met, such as finite possible states within a given volume. Whether those conditions hold in the real universe is still debated. Even if repetition were implied, it would occur at distances so vast that they would be permanently beyond any horizon. From an observational standpoint, such regions might as well not exist. This brings us back to a recurring theme. Cosmology distinguishes carefully between existence and relevance. Something can exist beyond the observable horizon, and yet have no bearing on observable phenomena. From a scientific perspective, the question of finiteness versus infinity matters primarily for theoretical consistency. It shapes how cosmological models are constructed and how certain parameters are interpreted. It does not affect everyday observation or the structure within the observable universe. Another reason the question remains open is that cosmic topology is hard to detect. If the universe were finite and wrapped around itself, it might leave subtle signatures in the cosmic background, such as repeating patterns or correlations across large scales. Scientists have searched for such signatures. So far, none have been conclusively detected, but the absence of evidence is not evidence of absence. The universe could be finite with a topology too large to reveal itself within the observable region. There is also the issue of cosmic variance. We have access to only one universe, and only one observable region within it. This limits statistical certainty. Some features may simply be beyond our ability to measure precisely, because there is no way to repeat the experiment from different locations. This limitation does not undermine cosmology. It defines its scope. The finite versus infinite question also intersects with philosophical intuitions. Infinity can feel unsettling because it defies completion. Finite universes can feel more manageable, more contained. But nature does not arrange itself to satisfy intuition. Physics has already shown that many counterintuitive ideas are true. Time can stretch, space can curve, particles can behave like waves. Infinity may be another such concept, or it may turn out that the universe avoids it through subtle geometry. From a physical standpoint, both possibilities are acceptable as long as they are internally consistent and match observations. There is another angle worth considering. Even if the universe is infinite in spatial extent, it may not be infinite in all respects. It may have a finite age. It may have finite energy density. It may have horizons that limit interaction. Infinity in one dimension does not imply infinity in all dimensions. Similarly, even if the universe is finite in spatial volume, it may still contain an enormous amount of matter and energy, far beyond what can ever be observed. So the finite versus infinite question is not binary in the way it first appears. It has layers. One of those layers concerns predictability. In a finite universe, especially one that is small enough for global properties to matter, initial conditions could play a larger role in shaping outcomes. In an infinite universe, local conditions may dominate, with global structure becoming less relevant. This distinction affects how cosmologists think about probability and typicality. If the universe is infinite, then defining what is typical becomes more subtle. If it is finite, typicality may be easier to define, but only if the total volume is known. These issues matter most in theoretical work. For observational cosmology, the focus remains on what can be measured. At present, every reliable measurement suggests that within the observable region, the universe behaves as though it extends smoothly and uniformly. There are no signs of wrapping, repetition, or curvature strong enough to imply a small, finite universe. This pushes the likely scale of the universe. finite or infinite, far beyond the observable horizon. It is also worth noting that the question of finiteness may not have a final answer within current physics. New theories could change how space, time, and geometry are understood. Concepts like quantum gravity may alter the meaning of infinity itself. In that sense, asking whether the universe is finite or infinite is also a way of probing the limits of present knowledge. It highlights where theory meets observation and where speculation begins. What can be said with confidence is this: the observable universe does not require the universe to be finite, and it does not require it to be infinite. Both possibilities are consistent with everything observed so far. That may sound unsatisfying, but it is an honest reflection of the evidence. There is also a practical lesson here. For all the talk of infinity, the observable universe is already more than sufficient to challenge comprehension. Whether or not there is more beyond it does not diminish the scale we already have access to. In fact, the question of finiteness often distracts from a more grounded one. Given the size of the observable universe, how do scientists actually measure distances, ages, and structures within it at all? How is any of this known with confidence? Measuring something as large as the observable universe does not begin with rulers, tape measures, or direct traversal. It begins with inference, patience, and a careful layering of methods that build upon one another. Scientists do not measure the universe's size in a single step. They construct a distance ladder, rung by rung, using physical processes that can be tested locally, and then extended outward with increasing reach. At the smallest scales, measurement starts close to home. Distances within the solar system are determined using geometry and timing. By bouncing radio signals off planets and measuring how long they take to return, scientists can calculate distances with remarkable precision. These measurements anchor the scale of nearby space and establish the first reliable units. Beyond the solar system, direct timing no longer works, so astronomers turn to parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. This shift is tiny, often less than the width of a human hair seen from kilometers away, but it is measurable. From that shift, distances to stars within a few thousand light years can be calculated directly. Parallax is foundational because it is geometric and does not rely on assumptions about how stars behave. It provides a solid baseline. However, it has limits. Beyond a certain distance, the shifts become too small to detect reliably, even with the best instruments. To go farther, scientists rely on objects with known intrinsic brightness. If you know how bright something truly is, and how bright it appears from Earth, you can calculate its distance using the inverse square law of light. This principle states that brightness decreases predictably with distance. Certain types of stars serve this purpose exceptionally well. Some stars vary in brightness in a regular way, and the period of that variation is directly related to their intrinsic luminosity. By measuring how fast these stars brighten and dim, astronomers can determine how bright they truly are and thus how far away they must be. These stars act as standard candles. They allow distances to be measured across vast regions of our galaxy and into nearby galaxies. Crucially, they can be calibrated using parallax measurements for nearby examples, linking the distance ladder together. Beyond nearby galaxies, even brighter standard candles are needed. Certain stellar explosions release enormous amounts of energy and reach nearly the same peak brightness every time. Because they are so luminous, they can be seen across billions of light years. By comparing how bright these explosions appear from Earth to how bright they are expected to be intrinsically, scientists can measure distances to extremely distant galaxies. These measurements extend the distance ladder deep into the observable universe. Distance alone, however, is not enough to determine the universe's size. Expansion must also be measured. This is where redshift becomes essential. When light travels through expanding space, its wavelength stretches. Light that starts out blue can arrive redder. The amount of this stretching is directly related to how much the universe has expanded during the light's journey. By measuring redshift, scientists can infer how fast a galaxy is receding due to cosmic expansion. Redshift measurements are relatively straightforward once the light from a galaxy is collected. Spectral lines act as fingerprints, revealing how much the light has been stretched. The greater the redshift, the farther away the galaxy is, and the earlier in cosmic history the light was emitted. By combining redshift with distance measurements from standard candles, scientists can map out the expansion history of the universe. This relationship is not perfectly linear across all distances, because the expansion rate has changed over time. Accounting for that change is part of the challenge. The expansion history feeds directly into size calculations. Knowing how fast the universe has expanded at different times allows cosmologists to calculate how far away distant regions are today, even if the light we see from them was emitted when they were much closer. Another critical tool comes from the ancient radiation that fills all of space. This radiation carries information about the universe when it was very young. Tiny variations in its temperature reflect sound waves that travelled through the early universe's hot plasma. The size of these sound waves is known from fundamental physics. By measuring how large they appear on the sky today, scientists can determine the geometry and scale of the universe. This method acts like a cosmic yardstick, stretching across billions of light years. What makes this approach powerful is that it relies on physics tested in laboratories on Earth. The same laws governing waves and particles apply across the universe. This consistency allows small-scale physics to inform large-scale measurement. Large galaxy surveys provide another layer of measurement. By mapping the positions of millions of galaxies, scientists can identify characteristic patterns in their distribution. These patterns, imprinted by early universe processes, have known physical scales. Measuring how large those scales appear today provides additional distance information. Each of these methods has uncertainties. No single technique is perfect. What gives cosmology its strength is redundancy. Multiple independent methods converge on the same results. When different approaches agree, confidence increases. This convergence is especially important when dealing with extreme scales. Measuring distances across billions of light years involves extrapolation, but it is not blind extrapolation. Each step builds on previous ones, anchored by physics that can be tested closer to home. Time also plays a role in measurement. Because looking far away means looking back in time, scientists must model how the universe evolved between then and now. This modelling includes how matter clumped, how expansion changed, and how energy components influenced geometry. These models are not free inventions. They are constrained by observation. When predictions fail to match data, models are revised or discarded. Over time, this process has narrowed the range of possibilities and refined measurements. One challenge that remains is tension between different measurement methods. Some approaches yield slightly different values for the expansion rate today. This discrepancy is small but persistent. Rather than undermining cosmology, it highlights where understanding is incomplete and where new physics might emerge. Even with these tensions, the overall picture remains consistent. The observable universe has a finite, measurable size. Its scale follows from its age, expansion history, and geometry. What is remarkable is not just that scientists can estimate such a size, but that they can do so with meaningful precision. The uncertainty in the observable universe's radius is tiny compared to the radius itself. That level of precision would have seemed impossible a century ago. All of this measurement relies on one quiet assumption that has been tested repeatedly. The laws of physics appear to be the same everywhere. Light behaves the same, gravity behaves the same, atomic processes behave the same. Without that consistency, measurement across cosmic distances would be impossible. This assumption is not philosophical, it is empirical. Every observation so far supports it. So when scientists say the observable universe is about 93 billion light-years across, they are not making a guess based on incomplete data. They are summarizing the result of many overlapping measurements, each grounded in tested physics and observation. That does not mean the number is final. Refinements will continue. Parameters may shift slightly. New data may adjust the picture. But the scale itself is robust. Understanding how measurement works also clarifies why the observable universe is defined the way it is. It is not just a concept. It is a calculable region whose size can be derived from independent evidence. Long before stars ignited or galaxies assembled, the universe left behind a signal that still surrounds us today. It is faint, nearly uniform and easy to overlook, yet it carries more information about the universe's size, age and structure than any other observation we possess. This signal is known as the cosmic microwave background, and it marks the earliest moment in cosmic history that can be observed directly. To understand why this ancient light matters so much, it helps to picture what the universe was like before it existed. In its earliest stages, the universe was not transparent. It was hot, dense, and filled with charged particles. Light could not travel freely because it was constantly interacting with matter, scattering again and again in every direction. During this time, the universe behaved more like the interior of a star than the empty space we imagine today. Photons existed, but they were trapped, unable to move far before colliding with electrons and other charged particles. Space was filled with a glowing plasma, and no image could form because light had no clear path. As the universe expanded, it cooled. Eventually, after about 380,000 years, conditions changed enough for electrons and protons to combine into neutral atoms. Once that happened, light was suddenly free to travel. Photons that had been trapped were released and began moving through space largely unhindered. That moment is known as recombination, and the light released then is what we now observe as the cosmic microwave background. This light has been travelling ever since, over billions of years. As the universe continued to expand, the light stretched along with space. What began as visible and infrared light cooled and lengthened into microwave wavelengths. Today it arrives as a faint background glow detectable in every direction. The cosmic microwave background does not come from a single location. It comes from everywhere at once. No matter where you look, you are seeing light emitted when the universe first became transparent, arriving from the farthest distances we can observe. This is why it represents the ultimate observational boundary. Beyond this light, the universe is opaque to electromagnetic radiation. There is no older light to see, because earlier photons could not travel freely. In terms of the observable universe, the cosmic microwave background defines the farthest surface we can observe in time. It is often described as the edge of the observable universe, but that description can be misleading. It is not an edge in space. It is a snapshot of the universe at a particular moment in its early history, seen at different distances in different directions. Because light from that moment has been travelling for nearly the entire age of the universe, the present-day distance to the regions that emitted it is about 46 billion light-years. This is how the cosmic microwave background helps define the observable universe's size. But its importance goes far beyond marking distance. When scientists first detected this background radiation, it appeared remarkably uniform. The temperature was almost exactly the same in every direction, differing by only tiny amounts. This uniformity was a major discovery because it confirmed predictions made by models of an expanding universe. Those tiny variations, though small, are crucial. They represent slight differences in density in the early universe. Regions that were slightly denser would later become the seeds of galaxies and clusters. Regions that were slightly less dense would become voids. In other words, the cosmic microwave background is a map of the universe's initial conditions. By measuring these variations with extreme precision, scientists can extract detailed information about the universe's composition, geometry, and expansion history. The size of the variations, their distribution across the sky, and their statistical properties all encode physical parameters. One of those parameters is the total energy density of the universe. Another is the proportion of matter, dark matter and dark energy. Another is the curvature of space itself. What makes this possible is that the physics governing the early universe is well understood. The behavior of plasma, radiation, and sound waves in hot, dense conditions can be modeled using tested physical laws. Those sound waves left imprints in the cosmic microwave background that act as standard rulers. The size of these imprints is known from physics. Measuring how large they appear on the sky today tells scientists how much space has expanded since that early time. This directly constrains the size of the observable universe. The cosmic microwave background is therefore not just old light, it is a measuring tool. It is also remarkably consistent. Different satellites and experiments have measured it using different instruments, different methods, and different frequencies. All converge on the same picture, the same temperature, the same variations, the same underlying patterns. This consistency is one of the strongest reasons cosmologists have confidence in the current model of the universe. Another important aspect of the cosmic microwave background is that it shows no preferred direction. There is no gradient pointing toward a center or an edge. Once local motion is accounted for, the background looks the same everywhere. This reinforces the idea that the universe is homogeneous and isotropic on large scales. It supports the view that our location is not special and that the observable universe is representative of a larger whole. The background also provides insight into the age of the universe. By analysing its properties, scientists can calculate how long it has been since recombination occurred. Combined with expansion models, this leads directly to the age estimate of about 13.8 billion years. Without the cosmic microwave background, this number would be far less secure. It also helps constrain inflation. The pattern of fluctuations in the background matches predictions made by inflationary models about how quantum variations would be stretched to cosmic scales. While this does not prove inflation in a strict sense, it strongly supports it. From the perspective of scale, the cosmic microwave background ties together several threads we have been following. It sets the maximum look-back time. It defines the largest observable distance. It encodes the universe's geometry. It reflects the processes that shaped structure. It is the foundation on which measurements of the observable universe rest. There is also a subtle point worth emphasizing. The cosmic microwave background does not come from a single spherical shell at a fixed distance. Different regions of the background we see today come from slightly different distances and times, depending on direction and local conditions in the early universe. So even this oldest light is not a perfectly uniform snapshot. It has depth, structure, and complexity. That complexity allows scientists to test fine details of cosmological models. Small deviations from expected patterns can signal new physics or refine existing parameters. In that sense, the cosmic microwave background is not a static relic. It is an active data set, continually reanalyzed as techniques improve. Despite its importance, it remains invisible to human senses. We cannot see it with our eyes. We cannot feel it. It fills the room you're in right now, passing through walls, bodies, and instruments unnoticed. It is only detectable with sensitive equipment tuned to microwave frequencies. This invisibility makes its impact easy to underestimate. Yet it is one of the most informative signals ever measured. The existence of this background also places a hard limit on what electromagnetic observation can achieve. There is no light older than this that can reach us. Beyond recombination, the universe is observationally dark in electromagnetic terms. This does not mean nothing existed earlier. It means that earlier information is inaccessible through light. Other messengers, such as gravitational waves, may carry information from earlier times, but those remain challenging to detect. So the cosmic microwave background marks the beginning of observational cosmology in a literal sense. It is where the universe first became visible. Everything we see beyond that point, galaxies, stars, quasars, all appear later in cosmic history. They are layered on top of this ancient backdrop. From a scale perspective, the background reinforces the idea that the observable universe is not arbitrary. Its size is tied directly to physical events in the early universe. The distance to the background is not guessed. It is calculated from known processes. That distance, combined with expansion, defines the observable horizon. Another interesting consequence is that the observable universe grows older, but not necessarily larger, in the way intuition expects. As time passes, we continue to receive light from regions slightly closer to recombination, but accelerating expansion limits how much farther the horizon can extend. So the cosmic microwave background will always represent the earliest visible moment, even as the universe ages. This gives the observable universe a built-in ceiling. No matter how long we wait, there will always be a time before which light cannot reach us. That ceiling shapes everything we can know. At the same time, the background provides a kind of unity. No matter where you are in the universe, if you could observe deeply enough, you would see a similar background surrounding you, marking the same early epoch. This symmetry reinforces the idea that the observable universe is centered on the observer, but governed by universal laws. As this picture settles, it becomes clear why the cosmic microwave background is indispensable. Without it, the size, age, and structure of the observable universe would be far more uncertain. With it, those properties become measurable. If the oldest light sets the ultimate observational boundary, and if everything we see is layered between that boundary and the present, then how does all of this feel when filtered through a human mind? How do people make sense of such scale without losing orientation? It often happens quietly, almost without notice. After hearing numbers large enough to fill pages with zeros, after tracing structures that stretch for hundreds of millions of light years, something inside the mind stops reacting the way it used to. The universe does not keep feeling bigger. Instead, it can start to feel strangely small, not because it is shrinking, but because the human mind has reached the edge of how it processes scale. This response is not a failure of understanding. It is a feature of cognition. Human perception evolved to handle distances measured in steps, minutes, or days of travel. Our brains are good at comparing the size of a tree to a house, or a hill to a mountain. Even continents and oceans can be grasped indirectly because they connect to lived experience. Cosmic scale does not connect in that way. It arrives only through language, numbers, and abstraction. When someone hears that the observable universe is about 93 billion light-years across, the number itself is registered correctly. But the meaning does not grow proportionally. After a certain point, adding more zeros does not make something feel larger. It simply moves it into a category labelled very big, where distinctions blur. This is why, paradoxically, the universe can begin to feel conceptually smaller as its size increases. Once it exceeds intuitive scale, it becomes a single mental object rather than a layered one. A galaxy, a cluster, and the observable universe can start to feel like variations of the same idea instead of radically different scales. Psychologists sometimes describe this as scale saturation. Beyond a certain magnitude, the brain stops tracking proportional differences. 10 million and 10 billion no longer feel distinct in the way 10 and 100 do. The numbers are understood symbolically, but not experientially. This effect explains why cosmic discussions can feel oddly calming rather than overwhelming. Once the universe passes beyond the range where the mind tries to map it onto physical experience, it stops triggering stress responses. There is nothing to brace against. The scale becomes distant in a literal cognitive sense. In this way, the vastness of the universe does not press inward, it recedes. There is also a related effect involving reference points. In everyday life, size is understood through comparison. A car is big compared to a bicycle. A city is big compared to a town. In cosmology, those reference points evaporate. The observable universe is not just bigger than familiar objects, it is bigger than comparison itself. Without anchors, the mind adapts by compressing. The universe becomes one object with a label attached, rather than a space that must be navigated mentally. This compression can make the observable universe feel oddly manageable. Once it is framed as a sphere with a defined size, even a staggering one, it acquires boundaries in thought, even if not in reality. Something infinite or indefinite is harder to hold mentally than something finite but enormous. So learning that the observable universe has a measurable diameter can make it feel smaller than an infinite unknown would. Measurement, even of extreme things, creates containment in the mind. Another factor shaping perception is familiarity through repetition. Early exposure to cosmic scale can feel shocking. Hearing about billions of years or trillions of stars for the first time often produces awe or discomfort. Over time, repeated exposure normalizes those figures. They become background knowledge rather than active surprises. This normalization does not mean the universe has become less vast. It means the mind has adapted. The same process occurs in other domains. People who work with large data sets stop reacting emotionally to large numbers. Astronomers regularly discuss distances that would paralyze intuition if encountered fresh. Familiarity creates calm, not because the scale is smaller, but because it is no longer novel. There is also a linguistic effect at work. Words like galaxy, cluster, and universe function as containers. They allow complex structures to be compressed into single terms. Once compressed, those structures become easier to handle mentally, even if their contents remain vast. Language in this sense acts as a kind of cognitive gravity, pulling sprawling ideas into manageable forms. This is not deception, it is efficiency. Another reason cosmic scale can feel smaller than expected is that it does not demand action. Vastness in everyday life often implies effort. A long distance must be crossed. A large object must be moved or avoided. Cosmic scale offers no such demand. There is nothing to lift, travel, or escape. The universe does not require a response. It simply exists. Without a call to action, emotional intensity softens. The mind observes rather than reacts. This detachment is reinforced by the fact that cosmic scale has no direct consequences for daily life. Whether the observable universe is 80 or 100 billion light-years across does not change how gravity behaves on Earth, or how time passes in a room. The scale remains intellectually significant but practically inert. Because of this, the universe's size can be contemplated without triggering urgency or fear. It is large, but it is not pressing. There is also a deeper psychological pattern involved. Humans naturally center experience on themselves. This is not arrogance, it is how perception works. Everything is filtered through a single point of awareness. When cosmology shows that every observer sits at the center of their own observable universe, it inadvertently aligns with this instinct. The universe feels centered around the observer not because it is, but because observation is structured that way. This alignment reduces cognitive dissonance. The universe may be vast, but it is arranged in a way that feels familiar to perception. In contrast, a universe with a visible center elsewhere might feel more disorienting. The absence of a preferred center allows the mind to settle into its own frame without conflict. Another subtle influence comes from time. Cosmic scale unfolds over billions of years. Human experience unfolds over seconds and decades. When time scales differ by so many orders of magnitude, the mind separates them into different categories. Cosmic time becomes abstract time, no longer competing with lived time. This separation reduces emotional interference. Events billions of years ago or in the distant future feel insulated from personal concern. The universe becomes something to think about, not something to manage. This insulation can create a gentle distance that makes cosmic ideas suitable for reflection rather than reaction. Scale becomes contemplative rather than alarming. There is also a paradox worth noticing. While cosmic scale can make individual concerns feel small, it does not necessarily diminish their importance. The mind is capable of holding multiple scales of meaning at once. A small experience can remain significant even when placed against a vast background. In fact, contrast can enhance meaning rather than erase it. Knowing that the universe is immense does not negate local experience, it contextualizes it. This is why people often report a sense of calm when thinking about the universe at large. Problems that feel overwhelming on a personal scale can loosen their grip when placed inside a broader context, not because they are unimportant, but because they are no longer isolated. Cosmic scale provides perspective without judgment. There is also an interesting asymmetry in how size is perceived. Very small scales, like subatomic particles, can feel more unsettling than very large ones. The idea that reality is built from things far beyond sensory access can provoke discomfort. The universe's largeness, by contrast, often feels open rather than intrusive. This may be because large scales remain external. Small scales feel as though they undercut reality from within. So the observable universe, despite its size, does not threaten the coherence of experience. It expands outward rather than dissolving inward. Another element shaping perception is the smoothness of cosmic laws. The same physical principles apply across the observable universe. There is no chaos at large scales. Expansion is orderly. Structure formation follows predictable patterns. This regularity creates cognitive stability. If the universe were vast and lawless, scale might feel frightening. Instead, it is vast and structured. This structure allows the mind to rest. There is no need to track infinite variation. Patterns repeat. Statistics apply. Predictability exists. Even the idea that most of the universe is empty contributes to this calm. Emptiness reduces perceived threat. The observable universe is not a crowded, pressing space. It is sparse, with islands of matter separated by vast distances. This sparsity mirrors quiet. It invites contemplation rather than alarm. There is also a narrative effect at play. Cosmology presents the universe as a story unfolding over time, from simplicity to complexity. Stories are easier to process than static immensities. The universe becomes a sequence rather than a monolith. When scale is embedded in narrative, it becomes digestible. The mind can follow change more easily than it can hold a fixed infinite. So the observable universe feels smaller not because it is, but because it is explained. Explanation tames scale. Another reason scale feels less overwhelming is that cosmology often emphasizes boundaries of knowledge. The observable universe is explicitly limited. There are horizons. There are things we cannot see. Paradoxically, knowing there are limits reduces cognitive load. An unlimited universe without observational boundaries would be harder to conceptualize. A universe with a defined observable region offers closure, even if that closure is partial. The horizon gives shape to ignorance. It says, this is what can be known directly. That clarity is calming. There is also an emotional resonance in knowing that every observer has their own observable universe. It means no one is excluded from the cosmic picture. No matter where you are, the universe unfolds around you in the same fundamental way. This universality creates a sense of belonging rather than insignificance. The mind responds differently to being small in a vast system than to being irrelevant in one. Cosmology suggests the former, not the latter. We are small in scale, but not extraneous. This distinction matters. As these psychological layers accumulate, the observable universe becomes something that can be held gently in thought. Its size does not need to be wrestled with. It can simply be acknowledged. That acknowledgement often brings stillness rather than agitation. There is a reason why thinking about the universe late at night feels different than thinking about it in the middle of a busy day. When attention slows, scale stops competing with immediate concerns. It becomes background rather than foreground. In that state, the universe does not feel like a challenge. It feels like context, and context does not demand resolution. Understanding how the human mind responds to cosmic scale does not diminish the science. It completes it. Measurement tells us how big the observable universe is. Psychology tells us how that information is lived with. Together, they explain why something so enormous can feel so quiet. Somewhere between the largest numbers we can name and the quiet moment you're in right now, the observable universe continues doing what it has always done. Space stretches, light travels, time moves forward without asking to be noticed. And while nothing about that process depends on our attention, there is something uniquely human about pausing to notice it anyway. By this point, the idea of the observable universe may no longer feel sharp or overwhelming. It may feel rounded, settled, almost familiar in its vastness. Not because it is small, but because it has been traced carefully, layer by layer, without rushing toward conclusions or forcing it into a single image. The observable universe is large, but it is also specific. It has a size that can be calculated. It has a history that can be reconstructed. It has limits that can be described without implying an ending. It is not everything that exists, and it does not need to be. That distinction matters more than it might seem at first. What we call the observable universe is not a claim about ultimate reality. It is a statement about connection. It marks the region of the universe that has had time to interact with us through light and physics. It is the portion of the cosmos that has, in a very literal sense, reached out and made contact. Everything within it is linked by shared history. The light arriving from distant galaxies left its source billions of years ago, crossed expanding space, and arrived here carrying information about how the universe once was. That connection is fragile, delayed, and incomplete, but it is real. Beyond the observable horizon, reality likely continues. Space does not suddenly empty, time does not stop, the universe does not end just because our view does. What ends is our ability to receive signals, to gather evidence, to confirm directly. This is not a shortcoming of curiosity or technology. It is a feature of how the universe works. The horizon exists because the universe has a finite age and a finite speed for information. Those two facts together define everything we can ever observe. They give the observable universe its shape, and that shape is not static. As time passes, the observable universe changes. Light continues to arrive from regions that were once beyond reach. At the same time, accelerating expansion ensures that some regions we can see now will eventually fade away. Their future signals stretched beyond recovery. So the observable universe is not a fixed container. It is a living boundary, constantly renegotiated by expansion and time. This makes it less like a box and more like a shoreline. The water moves, the horizon shifts, the land beneath remains. Standing at such a boundary can feel paradoxical. On one hand, it emphasizes limitation. There are things we will never see. On the other hand, it highlights abundance. Even within those limits, the observable universe contains more structure, more history, and more scale than intuition can fully absorb. There are hundreds of billions of galaxies within this region, trillions upon trillions of stars, vast webs of matter shaped by gravity, ancient light carrying echoes of the universe's earliest moments, and yet none of that presses in on the present moment. Right now, wherever you are, the observable universe includes you without demanding anything from you. It does not require comprehension to continue existing. It does not need to be visualized correctly to remain vast. The universe does not test us on whether we understand it. It simply is. That realization can bring a sense of quiet relief. The scale of the cosmos does not create responsibility. It creates context. You're not required to hold the whole universe in mind. You're allowed to let it be large without trying to master it. In fact, one of the most honest responses to cosmic scale is to stop reaching outward and allow perspective to settle inward. The universe does not become smaller when attention turns back toward the present. It becomes integrated. The same physics that governs the expansion of space also governs the atoms in the room around you. The same laws that shaped galaxies shape the elements in your body. There is no sharp divide between cosmic and local. There is only scale, and scale does not diminish relevance. The observable universe may be nearly 93 billion light-years across, but the moment you are experiencing now is not made less meaningful by that fact. It exists on a different axis, not a lesser one. Cosmology often gets framed as a humbling discipline, and it is, but not because it reduces everything to insignificance. It humbles by showing continuity. The same universe that contains unimaginable distances also contains quiet rooms, slowing breath, and moments of reflection. Those things are not in competition. If anything, the size of the observable universe makes the existence of calm moments more remarkable, not less. There is also something reassuring about knowing that no matter how far outward we look, the universe remains governed by the same rules. It does not become chaotic at scale. It does not abandon structure. It does not dissolve into unpredictability. Expansion follows equations, light follows paths, matter responds to gravity. Patterns repeat. That regularity allows curiosity to rest. There is no urgency to solve everything immediately. The universe has been unfolding for billions of years. It is not waiting for conclusions. In that sense, the observable universe invites a different relationship with knowledge. Not conquest, not completion, just continued observation. The horizon will always be there. The boundary of observation will always exist. And that is not a flaw in the universe. It is what gives observation meaning at all. Without limits, there would be no structure to knowing. Without horizons, there would be no perspective. So drifting at the edge of the observable universe does not mean standing at the brink of something ending. It means acknowledging where connection fades into inference, where evidence gives way to possibility. And possibility does not need to be resolved to be meaningful. Beyond the horizon, the universe likely continues in much the same way it does here. More space, more matter, more time. But none of that needs to be settled tonight. What can be settled is the idea that the observable universe is not a threat to comprehension. It is an invitation to slow thinking, to curiosity without pressure, to perspective without urgency. You're allowed to let the numbers soften. You're allowed to stop visualizing distances. You're allowed to let the universe remain large without forcing it into clarity. Science does not require constant engagement. It benefits from rest, and rest does not mean disengagement. It means allowing ideas to settle into background awareness, where they can exist without being actively processed. Right now, the observable universe includes every place light has had time to reach from since the universe became transparent. It includes ancient radiation still passing silently through space. It includes galaxies whose light began its journey before Earth existed. It also includes this moment, not because this moment is special in cosmic terms, but because observation always begins here. That fact does not elevate or diminish anything, it simply connects, and connection is enough. So as attention eases and thoughts begin to drift, the universe does not need to be held tightly. It can remain vast, structured, and quietly ongoing, whether or not it is being actively considered. The edge of the observable universe is not something to stand at. It is something to be aware of, gently, without expectation. There will always be more to learn. There will always be unanswered questions. There will always be regions beyond reach. None of that prevents understanding from being meaningful where it exists. For now, it's enough to know that the universe is large but not infinite to your experience, that it is bounded by time, not walls, that it continues beyond what can be seen without needing to be imagined precisely, and that wherever you are, the observable universe unfolds around you in the only way it ever can, centered on your position in space and time, not because you are central, but because observation itself is. Nothing needs to conclude here. The universe will keep expanding, light will keep travelling, horizons will remain where they are, and curiosity can rest, knowing that even at the edge of what can be seen, there is no pressure to go further tonight.